Okay. Okay, can you hear me now? Coming over the speakers, he says yes. Okay, great. Sorry about that, but hopefully you're able to follow along. We haven't really gotten too far in yet. Just want this to disappear down here. I guess that's just the chat, maybe. Okay, well, I apologize if some stuff gets cut off at the bottom. Okay, so where were we? Talking about simple problem of flipping a coin some number of times and then estimating the probability that we're going to see heads on the next flip. So what we're going to try to do is develop a bound on the error of our estimate. And intuitively, as you flip the coin more and more times, you gather more and more data, you get a better estimate of what the true probability of heads is. So formally speaking, we're going to try to prove, we're going to assume that there is some true probability of coming up heads. We'll call that mu. And we have an estimate mu hat, and we want the absolute value, for example, between those two things to be small with a very high probability as n gets larger and larger. This is, by the way, again, just throwing some more jargon out there. Basically, everything that you see today is going to be more or less taking this kind of like frequentist notion of statistics. A lot of these ideas transfer over to the Bayesian setting, but I just want to mention that at the beginning for those of you who've heard those terms before. The idea behind a frequentist interpretation of probability is that there is this true underlying probability of coming up heads mu when we're trying to estimate that in a kind of point-wise sense. So that's going to be our framework, and in order to characterize how well we are able to estimate the true probability of heads, we're going to specify two things. The first thing you're going to specify is a parameter epsilon, which what you can think of as being our target level of accuracy. Do we care about estimating the probability of heads within 1%, or are we okay with 10%? It might depend on the application and the specifics of your data. And then the second thing you're going to specify is a failure probability, which we're going to call delta. And the way there's several ways to think about this, but the way that I think I like to think about it, at least if I want to simplify things, is I'm going to think about fixing my epsilon to something like I care about estimating the true probability up to 5%, and then given that, there's going to be some probability that I succeed for each n. So you can think of this failure probability delta as being a function of the amount of data that you collect. And again, intuitively, as you collect more and more data, your failure probability is going to go lower and lower and lower because you're going to converge to the true probability. And the question is, how rapidly does this delta function converge to 0, more or less? Okay. And again, throwing out bits of jargon because I think it's useful to just get exposed to this stuff. A lot of people will call these kind of proofs or these error bounds epsilon delta proofs because these epsilon and delta parameters show up a lot. So if you've heard epsilon delta proofs, this is exactly what we're going to be talking about. Okay. It's like really unfortunate that this is going to get cut off. Okay.
I think if you go to view options.
View options, thank you. I'm not a Zoom super user. Is it right? Let's see, hide video channel? No. Hide.
Maybe
can you just double click it to make it non-full screen and then go back and then double click it again? Like the main. Oh.
It's great because I feel like Zoom fit just went. I thought that this like wasn't showing earlier for some reason. I feel I just did a chat. Oh, I think I can drag this actually. Oh.
Oh yeah, I think it might have been just because there was a chat message. But then
It might have been, and then okay, yeah, there we go. That's so if I don't touch it, and nobody else enters anything into the chat. Okay, sorry. Thanks for bearing with me on this, but again, we have plenty of time this morning, so plenty of interruptions are fine. Okay, so what we're going to be able to show for in a lot of cases is that this failure probability delta decays to zero exponentially quickly. So delta, in other words, this failure probability delta of n is going to be proportional to an exponential function raised to the negative n. And that's really fast and useful in a lot of cases. So for example, I mean, I work in neuroscience applications. There's not too many, there's no neuroscience applications built into this talk, but it's a very typical case is I'll be working with some experimentalist and they're recording neural activity in some animal that's trained to do a behavior. And that animal will like press a lever or something like this 20 times, and we'll make a measurement of the neural response. And its neurons are very, very noisy. So they'll look at this and say, well, the response is pretty variable. The average looks like this. You know, how much better can I do if I collect 20 more trials? And this is usually a very helpful thing to be able to tell them, like, your regression model is going to converge exponentially quickly, you know, the more trials you get. And, you know, depending on the particular details of your model or the particular details of the noise, you might not always be able to prove this and you might be converging slower. So we'll talk about that a little bit. Any questions on this overall setup? Okay. I guess one other thing, because I don't have a slide on this, is that we're going to be focused on proving bounds like this when n is finite. So one of the things that you'll learn, like if you took statistics in high school or you know, in your statistics 101 class in undergrad, like one of the first things you'll talk about is the central limit theorem. So the central limit theorem says that as n goes to infinity, the distribution of this mu hat converges to a Gaussian distribution, and the standard deviation of that, you know, depends on the variance and things like this, but also has kind of like exponentially decaying tails in some sense. And so the central limit theorem is very useful, but that only holds in the case where n goes to infinity, that Gaussian approximation. So the idea behind Chernoff bounds and the things that we're going to talk about is that we don't want to work in that asymptotic regime. We want to work in the real world where we only have 50 trials or something. So we're going to prove bounds that hold for finite n, and it could be, you know, n equals 10 or 100 or 1,000. They're just going to kind of be generally applicable, and we're not going to have to make assumptions about like asymptotic convergence to normality and things like this. That's actually very useful. It's maybe a subtle point, but this is something that if you took a statistics course or you were doing statistics research 50 or 70 years ago, everybody was working in this asymptotic regime. In modern statistics, we really don't like to do that for various reasons. Oh yeah, question.
Yeah, so does that bound assume that you can that you can sample in an unbiased manner?
Yeah. So I didn't state that assumption here. I'll state it in the future, but this bound is going to hold if the samples of your coin flips are independent and identically distributed.
Right.
IID.
And also, I guess the test time distribution is the same as.
Yes. Yes, exactly. Yeah. Yeah, there's various like impossibility results if your test time distribution is different. Going back to David Hume, really, it's not. You don't even need mathematics to prove it. Other questions? Good questions. Okay, so the next plot here is just a simple simulation that I ran on my computer. So one of the things I really like about these error bounds is that it's very easy to simulate data from the situation I just described, where you know the ground truth model. So I know the true probability of heads, for example. And then I can run simulations where I collect 50 trials or 100 coin flips or whatever, form this estimator of the mean and look at how far I'm off. So the y-axis here, I've set epsilon equal to 0.1, so I'm okay with estimating the probability of coming up heads within plus or minus 0.1 probability threshold. And if I only have a small, if I only see 2 coin flips, I have a reasonably high probability that I'm going to fail. Like, it's just really hard to estimate the probability of coming up heads if I have that few coin flips. But you see that this simulation is decaying what looks like exponentially fast. And there's all these weird ringing results, and that's because of weirdness with the threshold I set, and even and odd numbers or whatever, because you're just dividing by a slightly different integer each time. So this is actually a really complicated function. And the nice thing is that we can prove this upper bound on how quickly we're decaying. It's going to be kind of like a Chernoff-Hofting bound, as we'll see. And that gives us the right rate of decay, which is exponential. And this is an upper bound on the true probability of making a serious error. Okay, questions on that? Okay, so getting back to your question and thinking about formalizing this in a little bit more generality, we're gonna, generally consider cases where we're given some number of independent and identically distributed samples of an unknown distribution, and I'll call these kind of x1 up through xn. These are random variables. And in general, we're trying to estimate a quantity, call it theta. In the last example, this was the probability of coming up heads. Theta could also be the average or the mean of the distribution. It could be the covariance of the distribution if the x's are multidimensional measurements. This is actually something that I'm working on quite a lot recently, is the problem of measuring covariance matrices between different neurons. So if you have neural responses, each x1 through xn is the number of electrical impulses fired by a group of 100 neurons. You want to estimate the 100 by 100 covariance matrix. Theta could also be regression parameters. So you want to predict, some of the x's from the others, or predict y given x, this sort of thing. Theta, could be that. So this is exactly what I was just saying here, that theta can be, defined in many different ways. In all cases, we're going to specify some learning algorithm or learning procedure that takes in the data and gives us a theta hat. So this could just be taking the sample mean, for example. And then we're also going to specify an objective function that we want to minimize. So I think I have some examples here. You could think about if there is a true theta that you don't know, What is the quadratic loss between theta and theta hat, or the absolute value, which is what we considered in the previous coin flipping example. And when you get into more complicated regression models, what we'll see is a really nice loss function that we want to think about bounding is, or sorry, I shouldn't call it a loss function, I should call this an objective function. And in particular, this objective function is called a risk function, and it is the expected loss function of the regression. So you can think of this lowercase l as being a quadratic loss, or like least squares estimation of a regression model. And what we actually want to minimize or bound the error on is what is our expected loss on future data examples. So here, this expectation is taken over x and y pairs for that for additional things that we've seen, and this f function is some linear or potentially nonlinear regression function that predicts y from x. And we're going to optimize over the parameters of our model theta, get a theta hat, and we want ideally our theta hat to have minimal risk on future examples. Questions on that? Okay, so we're given data, we have a learning procedure, we specify some objective function that that relates to our application or the performance of our model. And then again, we're going to specify a level of accuracy epsilon. And then finally, the last step is going to be given a fixed level of epsilon, derive some upper bound function, which basically says that if our objective function, or the probability of our estimated parameters objective being more than epsilon away from the optimal loss is less than some delta probability. Okay, so that's the general setup of what we'll walk through. Okay, so the other thing before diving into how we actually do this is to say that this is a very, very broad topic, and this framework can be applied to many, many different models, and different models end up having different methods for upper bounding the probability of having an error. So we're not going to be able to cover all of those things today. What we are going to talk about is we're going to work through Markov's inequality, which is more or less the inequality that everything else is derived from. And then Chernoff bounds and Chebyshev's inequality, which I think follow pretty generally. We're not going to have time to get to these various other topics, kind of on the more theoretical side, but I can give you references. There's a couple nice and recent textbooks that really do a good job of synthesizing all of this material. But this first kind of part of the talk, although this is all going to be kind of blended together, really deals with a lot of dry mathematical machinery for doing these things. It's actually, I mean, this is what, if you get a PhD in statistics, you spend your days sitting at a desk working with these inequalities and really doing pretty hardcore, in my opinion, mathematics to like show the theoretical properties of different models and estimators. The second part, which is ultimately what I'm more interested in, is all the different applications of these mathematical tools. So this is just to say that I think there's going to be a few slides with a lot of equations, but I think it helps you get through those equations if you can see the light at the end of the tunnel. And again, this framework is very general, so you can apply it to give guarantees on how well we can estimate the mean and covariance of random variables. There's really interesting applications of these ideas to dimensionality reduction in PCA in the high dimensional regime. So the high dimensional regime meaning data where you have many, many features that you measure, but a small number of observations or trials. There's also this a really hot topic now in statistics is the idea of deriving error bounds in the setting where you have really heavy-tailed distributions, or even adversarial noise, where you fit some model to data from some distribution, but there's an adversary that is allowed to change that distribution to make your model fail as poorly as possible. It relates a little bit to the question you were asking. So the reason people are interested in this is both because the math is hard and interesting to people who do math for a living, or only math for a living, but it's also got interesting real world applications. You know, if you can imagine putting things like self-driving cars or other machine learning algorithms, deploying them in the real world, you want them to be robust to rare outlier events. And it turns out that a lot of these inequalities don't necessarily do that great in the presence of rare but extreme outliers. So we'll get some intuition for that. And then, yeah, at the end of this talk, we're going to talk about empirical risk minimization. So I just told you what the risk of a estimator is on the previous slide, and we're going to talk about empirical risk minimization over a finite hypothesis set. And this this applies to like a simple model of bounding the error on a regression function. And the math gets a little bit hairier when you extend it to an infinite class of hypothesis models or candidates models, but we'll talk about that at the end. And this is just to say that I'm only going to be able to give you a taste of real statistical learning theory in this talk. Okay. So let's dive into the meat. That's kind of the end of the introductory salvo. So if there's any questions, like high level questions, this would be a good time because math is going to start going on the slides. All right. So does anybody here know Markov's inequality? Like, I'm curious. Okay, there's not too many. I know that's a very broad, background of people. So this is why it was a little challenging to come up with the right set of notes. But Markov's inequality is more or less the it's really the foundation of this entire field. So we're going to walk through this pretty slowly and in some detail. So, okay, recall our setting. We have some objective function L on our estimator theta hat, and we want to find bounds like this so that the probability that our loss is greater than epsilon is less than delta. So here's a fact. If I have a non-negative random variable, call it z, then it holds that the probability that z is greater than epsilon for any choice of epsilon greater than 0 is going to be less than this. It's going to be less than the expected value of z divided by epsilon. Expected value is of course, just the mean. I'm assuming people kind of have a little bit of basic probability in statistics. So if I say anything that doesn't make sense or you haven't heard of, please interrupt. Okay, so this is Markov's inequality. And it's remarkably general. The only assumption we made is that z is a non-negative variable, and then this holds. And the really nice thing is that in typical cases, our loss function is going to be something that is lower bounded. Like, we can't have infinitely negative loss or objective function. So we can always, rescale by, adding a constant onto our objective function so that its minimum is equal to 0. So that would mean that if you think of your loss over your prediction of theta hat, that is a random variable and it's non-negative. So Markov's inequality is more or less always going to apply to the setting that we've set up. Does that make sense with everyone? It is actually a little bit, you have to think through it a little bit, you know, depending on your background, especially, you know, if people are more used to Bayesian perspectives. Like we're going to be thinking of theta hat, which is our estimate, as a random variable. And it's a random variable because it inherits the randomness of the sample x1 through xn. So that's just an important thing to kind of keep in mind throughout all of this, is that theta hat and L of theta hat is, we're treating it as a random variable. Yeah.
So I don't see how this value is between 0 and 1, or don't you need this?
It doesn't, yeah, so it's an upper bound.
Right.
So it can be a vacuous bound. It can be above 1. In fact, I'll go back quickly and show you. So this was the upper bound on the probability of failure, and you know, up until a certain point, it's actually above 1, so it's vacuous. But what we really tend to care about most is whether it's converging at the right rate. And I'll show plots later where you have a logarithmic axis on the y plot, and you can see, you know, these bounds are actually pretty tight.
Does it make sense to say the probability is less than 2?
Yeah, I mean, the probability is always less than 2.
Yeah, but you know.
So if you want, this is where a picture might help. If you have n on the x-axis and you have your probability on the y-axis, and this is my, you know, this is my one of my upper bounds. I have another upper bound, which is that the probability is always less than 1.
Yeah.
So I can really say that my error probability is the minimum of these two things pointwise. So it's, but yeah, this is what I was saying. Like this, in this region, the Markov inequality or bound is going to be vacuous. But what we really care about is, as n is getting pretty big, how quickly are we converging? Good observation and question. Okay. So it's remarkably easy to prove this. I think when I first saw it, I thought there was, oh, there must be something kind of tricky or magic going on here, but it's actually pretty easy to prove this. So we're gonna walk through it because I think it's so fundamental. Okay, so that's Markov's inequality in the upper right. And first I want to give you some intuition for why this inequality holds. So a nice strategy when you see things like this is to break it down by thinking about a simple case. So let's just say that epsilon is equal to 1. Then Markov's inequality simplifies to something like this. The probability that z is greater than 1 is less than its expected value. So what happens if we didn't have this? What happens if the probability of z being greater than 1 was actually, you know, greater than the expected value? What ends up happening here is that we have a contradiction. If this was true, then the expected value would need to be pushed further to the right or more positive. So to see this, you can write the expected value of z. This is just the definition of expected value. People have taken measure theory. There's a bit of subtlety here in how you define the integral, but we're definitely not going to talk about that because it doesn't matter. So this is the expected value of z. And remember, z is not negative, so I'm integrating from 0 to infinity here. So this is greater than or equal to, if I just shorten the bounds of integration from 1 to infinity, right? Because I'm always adding positive numbers here. So I can just, rather than integrating over everything, I can integrate from 1 up to infinity. And now I can also, rather than adding up positive numbers z greater than 1, I can just, every time I encounter a z greater than 1, I can replace it with something smaller, which is 1. So that's greater than or equal to, I just took the z here and set it equal to 1. So now I'm doing this integral from 1 to infinity of the probability of z, or the probability density of z. And by definition, that is the probability that z is greater than or equal to 1. So we've proved in this simple case that the expected value of z has to be greater than or equal to the probability of z greater than or equal to 1. Any questions on any of those steps? Okay, so now let's do it for general epsilon. It's basically the same exact argument. So this inequality up here only holds, I can, if and only if I, multiply both sides by epsilon, I get this expression. This is just the equivalent way of stating Markov's inequality. And we're just going to go through the same sequence. So again, we're going to start with the expected value of z. We're going to, give the definition of what the expected value is. Now I'm going to replace the limits of integration from epsilon to infinity rather than 0 to infinity. Again, this works because epsilon is anything greater than 0. Now I replace the z with an epsilon. Now the epsilon can get pulled out of the integral because it's just a constant. And then I'm left with this integral from epsilon to infinity of pz. So I get this probably. Yes?
So how do you know that when you replace the z with epsilon, that
Yeah.
it's greater than, I mean, you're kind of already putting in there that your expected value of z is greater than epsilon, right?
So this step here, right?
Yeah, why does it work?
So that works because, so you can think of this as a big sum of positive numbers starting at epsilon and going up to infinity, where epsilon is a positive number. So at the lower limit of integration, z is going to be equal to epsilon. At the upper limit, the z is going to be a bigger and bigger number than epsilon. So yeah, this is going to be greater than this because I'm replacing z, because basically z is less than or equal to, z is greater than or equal to epsilon between these bounds of integration. That's the,
I was just thinking about any variable, but it's actually the axis, that axis value.
yes, exactly. Yeah. Yeah. So the reason all these steps work again is because epsilon is a positive number and z is being integrated over the positive real axis. If you had negative numbers to worry about, none of this really works. So that was why that was a key assumption for us. Thanks for that question. Good questions. Other questions on this proof? Okay, so again, I think I get really excited when there are easy proofs that have really big consequences. So I'm going to show you another proof because I think this is also a really useful way to think about it. So I'm going to start by defining an indicator function, which takes in a value z, and it's equal to 0 if z is less than epsilon, and it's equal to 1 if z is greater than or equal to epsilon. So again, this is just a step function over the z axis. Now I can write the probability that z is greater than epsilon as the probability density of z times this indicator function, and then integrate over all the real numbers. So when z is less than epsilon, this is going to evaluate to 0. That's going to contribute nothing to the integral. When z is greater than or equal to epsilon, I'm going to add up the probability densities of Z, and then sum those all together. That's by definition of the probability density, the probability that Z is greater than epsilon. Okay. So now what we're going to notice to prove Markov's inequality is that this step function is upper bounded by this linear function, Z divided by epsilon. So as a result, I can prove Markov's inequality by taking this integral and substituting this Z over epsilon upper bound on the indicator function. And now again, the 1 over epsilon is a constant, so I can pull that out of the integration. And what am I left with? I'm left with Z times P of Z integrated over the domain of Z, and that's just the expected value of Z, this integral. So now I have expected value of Z over epsilon, and I've given an alternative proof of Markov's inequality. Okay, that's a similar argument that we just walked through. It's maybe a little bit more complicated because I had to define this indicator function and all of this. So why am I telling you this? I think there's a really nice geometric intuition for this, which is that if I have some probability distribution over Z and I have this density function as shown here, I can think of this step function or this indicator function as the red line here. And when I integrate with respect to this measure, the density function of Z, when I integrate this step function, I get out the probability that Z is greater than epsilon. And then this upper bounded function, which is this nice linear function, when I integrate that with respect to the same probability density, I'm going to get the right-hand side of Markov's inequality. So this is, I think, I don't know, just kind of a useful way of pictorially or geometrically constructing a proof and thinking about it. So if the algebraic intuition doesn't make as much sense, you can maybe look at this picture and think about it for a while to help build some intuition. Yes?
And it tells us that Markov is like really loose, right? Like if you look at kind of like the distance between these functions is like going to infinity as
Yeah, no, it's true. I think so. I think it can be loose, but this is being recorded, so I'm like 99% sure that like Markov's is tight. Like it's definitely tight. Like you can come up with adversarial distributions over Z that saturate the bound.
oh yeah, no doubt about that.
Yeah. So then it's
Like maybe like maybe if you look like it's like like a logarithm, like the same idea, just kind of like something that passes through the corner and just doesn't go to infinity as instead of Z by epsilon, you can do something like
no, it's an interesting idea. I think the issue is, if you upper bound this with something more complicated, then performing this integral is no longer super easy. So that's like the real trick here, is that integrating with respect to this linear function is very easy. And yeah, I mean, I think like the issue that you eventually run into is that, so without further assumptions on Z, like I can't really do any better than this. So like in a sense, Markov's inequality is as tight as possible. If you only assume Z is non-negative, this is the best you can do. I'm again 99% certain that that's true. And we'll kind of go into other, like if you add assumptions on bits of the model, how you can get better and better bounds. But yeah, it's a good observation, and yeah, I honestly haven't thought too carefully about whether there is some other alternative upper bound that is tractable and outcompetes. I'm sure that somebody who was a full-time mathematical statistician or theoretical statistician could give a much better answer than I just gave, but Other questions?
Don't you get like Chebyshev's inequality if you apply like a quadratic bound? Right?
Yeah, so I think for Chebyshev's, so Chebyshev's is the very next thing. I'm not going to draw this picture, but yeah, you're going to draw a quadratic bound, or you can think of a quadratic bound. But in Chebyshev's, you actually don't make the assumption that it's not negative. So let's walk through it. And so Chebyshev's inequality. So okay, so once we have Markov's inequality, we can start doing a lot of pretty interesting things. So now I'm going to tell you another fact or theory of Chebyshev's inequality, which is if X is a random variable with mean mu and variance sigma squared, it doesn't have to be non-negative, then for any choice of epsilon greater than 0, you can prove that the probability that a realization of X is greater than epsilon away from the true mean is upper bounded by this quantity, sigma squared over epsilon squared. And the way that you prove this is very easy. Just define a new random variable z, call it, z, x minus mu squared. This is non-negative because I squared it. And now I'm going to apply Markov's inequality, and we're done.
Don't you need to? Oh no. I see where the square is coming from.
Where the square is coming from?
Yeah.
Oh yeah. So yeah, there's an absolute value there. So I think we're actually I have in my notes that in a moment we're going to work through one of these calculations together. But then the other bound we're going to talk about today is I'll call it a Chernoff bound. There's the very blurry line between Chernoff and Hofting bounds. There's kind of, I think Chernoff was the professor at MIT who kind of popularized this method, but Hofting technically did it first, but in special cases. So we'll call them Chernoff bounds, but sometimes I'll call them Chernoff-Hofting bounds. And then these are really, really useful, and often we'll see a little bit more useful than Chebyshev's inequality. So the statement of this theorem is a little bit more complicated, but we're going to, again, assume X is some random variable with a well-behaved moment generating function. So that's a bit of jargon that don't worry about that assumption too much. It'll become clear later. Then what Chernoff says is that for any choice of epsilon greater than 0 and also any choice of lambda greater than 0, you have this following bound. And just by looking at that, I think that you can kind of guess the method of proving this. So first, notice that the probability that X is greater than epsilon, this is true if and only if this holds. So I multiply both sides of this inequality by lambda, which is greater than 0, so that keeps the directionality of the inequality. And then I exponentiate both sides, that preserves the inequality. And now, so I have this, and then I apply Markov's inequality to this, and this is what I get. It's very simple. Yeah.
So the reason we need the exponential is because we don't have any assumptions on X being non-negative.
Yeah, X is not necessarily non-negative. Yeah, good point. X, but by exponentiating both sides, now they're non-negative, and I can apply Markov's. That's the exact idea. So the proof of this, yeah, it doesn't even. It's very obvious. As soon as you've proved Markov's inequality, you've kind of unlocked all this magic really easily. Okay, so let's work through a simple example together. Yeah.
Can you go? Yeah. Where did we need to take into account that the moment generating function is what we have here?
Oh, sorry. This so this is the moment generating function.
Right.
So this has to be defined.
Oh,
This
okay,
expectation doesn't exist for all
so
random
you just
variables.
need to be able to take the to take e to the power.
Yeah.
So that condition is equivalent to saying that all moments, finite moments of X are finite.
Yes. Yeah. Yeah. Yeah, it's just, yeah, this expectation exists, and if X is, I don't know, like a Cauchy distribution, I think you can't break down that expectation. Those are generally pretty, like, yeah, not so realistic cases, yeah, where you have exceptions to this. Okay, other questions on Chernoff and Chebyshev's inequality, how they follow from the Markov inequality. So let's walk through deriving an error bound on the sample mean. So let's say we have a data set x1 through xn. They're drawn IID. They have mean mu and variance sigma squared. And I'm not going to make any other assumptions on the data. And we want to estimate the mean of X. And again, we're going to kind of pick the most natural choice, which is just the sample mean. Again, this is something that people are really interested in the statistics community, is finding like better ways to estimate the sample mean when you have an adversarial noise or heavy-tailed distributions. But here we're going to do the sample mean, and we're going to derive a general bound on it. So again, the strong law of large numbers tells you that if you take n equals to infinity, this is going to converge eventually to the correct mean of the distribution of X, almost surely. And again, the whole point of the methods that we're talking about in this lecture are what can we say about how close mu is to mu hat for finite data. So let's work through how to use Chebyshev's to bound this error. And this will be a pretty simple calculation, but I want to take a break from speaking and have you guys write something. So if we apply Chebyshev's inequality, this tells us that this estimator, here I've plugged in. So again, the thing that you have to kind of keep in mind when applying these bounds is that you're going to think of your estimator as being a random variable. So this is my random variable that I actually computed from my data. And then I'm going to think about how far this is away from this estimator is away from its expectation. And then I'm going to put the variance of this was the sigma squared before in Chebyshev's inequality. So this is just writing out Chebyshev's inequality, applying it to mu hat of n as the random variable. That makes sense. And then what I want you guys to do now is to derive using, hopefully, if you've had a course in probability and statistics, what is the variance of this and the expected value of this? And then we're going to plug those in and see what we get. That makes sense? Does anybody need help, like knowing where to start on this? It's like totally okay. If, again, I think a lot of people here are from very different backgrounds, and for some people, this is probably their bread and butter. For other people, maybe they're not used to thinking about properties of expectation and such. I know it's early, yeah, but good job. Does anybody see people writing still? Somebody want to try for the expected value, or you guys want one more time to work through it? We're not in a rush. Let me do this one first, just because I think it's the idea. So the thing that you have to remember is that expectation is linear, so I can push this inside the sum. So I have this. And then each xi is drawn from the same distribution, and it has probability, or sorry, it has mean mu. So this is equal to 1 over m sum over I of mu. And the sum over I is going from I equals 1 to capital N. So this sum is equal to mu times n. So the n's cancel, and I get the expected value of mu hat is equal to the true mu. So this is an unbiased estimator, is the jargon that statisticians use to describe this. So, yeah.
Isn't that simply the definition of mu?
So the definition of mu is, well, so the definition of mu is kind of the limit of this, as n goes to infinity, of 1 over n, sum over I, xi. Like this is, in some sense, the definition of mu. But here we have mu hat, which is finite n. So the expectation here, like mu hat n is a random variable. Mu is a number. It's like a true property of the distribution. So there is a slight difference between mu hat and so what this is saying is that if I run the experiment many times independently and I collect n samples and I compute the sample mean, then on average across those independent data sets, my mu hat is going to be the expected value of mu hat is equal. So it is kind of I don't want to say obvious, but it's like, intuitively makes sense. But this is something that like kind of has to be proved in this way. Does anybody want to try the variance? Anybody figure out the variance? Want to do it? Okay. Trying to encourage interaction and take a break. I think I put it under here. So the variance of
so the variance doesn't scale linearly, it actually scales by the square. So if you have variance of Cx, because it's like expectation of x minus mu squared, this becomes C squared times variance of x. So yeah, C becomes C squared, so this becomes, over here C is 1 over n, so it becomes 1 over n squared. And since xi are IID, the variance of the sum is just the sum of the variances. So this is, and similar to this, like there's n of them, and each of them has kind of sigma square variance by definition, because they're all IID samples from a distribution with variance sigma square. N sigma squared by n squared, which is
Great. Yeah, that's exactly right. So, yeah, there's kind of two key properties here. The first is that, if you scale a random variable, that increases its variance by c squared. It's kind of intuitive because, variance has units of x squared. So you have to scale it by that. And then, this other property, if you have the variances of independent variables, just adds. And then, you simplify and you get squared over. So these are in summary, what you can derive for this estimator. Questions on that?
What is sigma squared?
Yeah, sorry. So each one of these random variables, xi, has expected value or mean mu, and variance sigma squared. So these are the true parameters of the distribution that defines x. And down here, when I'm deriving the expected value and variance, I'm deriving the mean and variance of a different random variable, which is defined by this expression. So it's the sum, or the average, empirical average of many of these x's. So yeah, mu and sigma squared is the mean and variance of a single xi, and what we were just kind of working through is deriving the mean and variance of a sum of x's. So two different random variables related to each other, obviously, but slightly different. And the reason this calculation, so this kind of showed us two things. The first is that this estimator is unbiased. The expectation of mu hat is equal to mu. The second is that the variance of this estimator is decreasing like 1 over n. So if I collect more and more data samples as n gets larger and larger, the variance is going smaller and smaller. So eventually, as n goes to infinity, I'm going to converge to a single point or delta function exactly on mu, and that's kind of the large, strong law of large numbers. So the 1 over n dependence is an important thing to kind of realize at the end of going through this mathematical exercise. Okay. So now plugging in these calculations we just did into Chebyshev's inequality, we're going to get the following bound on the sample mean. That square bracket is there, but that the absolute value of our error, the probability that we make an error greater than epsilon, is going to be upper bounded by this function sigma squared, which again is the variance of each individual realization, divided by n times epsilon squared. So there is a dependence on epsilon squared and sigma squared, but again, I think at least the first approximation, what we really kind of care about is how this failure probability is proportional to n. And basically, what this is saying is, as you collect more and more data, we're going to converge to zero probability of error, like 1 over n. So here is what that looks like. This is just a really simple simulation. Again, this is one of the things I like about these proofs is that you can kind of check them. I just simulated a bunch of data from a normal distribution with mean mu and variance sigma squared, just to check it out. And I ran this simulation many, many times. And what I'm plotting on the y-axis is the error between the sample mean and the true mean of the simulation. And you can see that that is going down. These dashed lines are kind of the upper and lower quartiles of this distribution. So remember, this is like one of the things about frequentist perspectives on statistical estimation is that this mu hat is a random variable. So I run the simulation many times for 10 samples, and I get a distribution here of my errors. So each slice through this is a probability distribution. And what Chebyshev's inequality in this case is telling us is that the probability that this error is larger than, we're basically trying to bound the tail probability of these distributions in the positive direction. So the probability that we're making a bad error. So this is kind of the raw simulation, and now here I've taken the outcome of that simulation and I've repackaged it in a way that is consistent with the epsilon delta proofs that we were just doing. So here I'm plotting, I chose epsilon equal to sigma. So epsilon is one standard deviation away from the mean. And I want to ask, what is the probability that my sample mean, my estimator of the mean, is wrong by one or more standard deviations? That's kind of, maybe reasonable error threshold that you might set. And what you see in the blue line here is the simulation. So the actual probability that I make an error decays to 0 pretty quickly. And then Chebyshev's bound here is decaying like 1 divided by n, which is what we just derived on the last slide. So this is an upper bound, and it's, not necessarily bad. It's giving us like a good insight. But for this particular case, at least, what we're going to talk about next is how we can actually do even better than this. It's generally the case that Chebyshev's is the best you can do, kind of similar to your question about Markov's inequality. The Chebyshev bound is generally viewed as kind of weak or loose. It's not loose because you can come up with kind of adversarial counterexamples that saturate the bound. I'll show a simulation of that later. Okay, so we're going to talk about Chernoff bounds and then talk about regression a little bit at the end. Before we do Chernoff, do people want like a 10-minute break or 15-minute break? Yeah. Okay. Let's break for break until 10:30, and then we can continue.
Question.
Yeah, sure. Questions?
Your work, like, do you actually use this bound to like say something about the number of points you need to gather for a certain error?
I think it's a good question. Like, as you get to more and more complicated models, like the results get more and more tricky, and typically there's constant factors that are hidden in these bounds that bring up this question of like how much do you rely on this in practice? I mean, in practice, you're going to use a lot of cross-validation to kind of get like a sense of how good your estimator is. But I think that this is still very useful because it gives you some intuition into the counterfactual statement, which is, okay, I designed this experiment and I collected 50 data points. And I do cross-validation, and like, honestly, my answers aren't so clear. Should I go back and do another experiment where now I collect 150 data points? So I think these general results give us good intuition for how much better like we would be expected to do if we reran the experiment. That's kind of, I think, one way in which I think of these bounds as being useful.
Many times people make more assumptions on the data itself and then try to say why these assumptions make sense, and then they just use the same bounds.
Like, can you give an example of that, or?
So if you, off the top of my head, so anyway, still the rest of that.
Okay, yeah. I mean, we're going to kind of do that in a minute, like where we're going to use Chernoff bounds, which make a stronger assumption on the tails of X.
Oh yeah, I meant on the distribution of X. Yeah, so
yeah, exactly.
So if you like, if you say that X is only built on a circle or something like this, then you can maybe do some stuff. I guess this is like what I saw that people use the effect
Yeah.
I was thinking more about like, I don't know, very expensive clinical trial. Like
Yes.
the manager tells you, okay, tell me like the minimum number of like data points I need to get to have a 90% accuracy.
Mhm.
I don't know if I would put my hands on fire and say, okay, the journal bound, yeah, you need like 125.
Well, I think it's also very difficult to do this for any new estimator, right? So for neural networks, you can do.
Well,
it
for
like
neural
two-
networks,
two
yeah.
layers and
Yeah.
that's it. Yeah, you're pretty much done.
Yeah. Yeah, I mean, there are real estimators that aren't neural nets.
Oh, yeah, yeah. For SVMs and linear regression and stuff, there are a lot.
Yeah.
From what I know.
Mhm.
But these bounds are not for like you said, they're for big ends, like for small ends, right?
Well, I mean, they're for all ends.
Yeah,
But
they're
yeah,
tighter.
they're tighter as you really kind of care about the scaling, I think, is one of the things. I mean, I think it also gives good intuition for things. So I didn't include slides on this because it's complicated enough. But again, one of the things I'm interested in is covariance estimation, and people in neuroscience, not just in my kind of field of systems neuroscience, but people who do fMRI and these other things, they measure signals from many different areas of the brain or many different neurons. So if you had n brain voxels that you're looking at, people are often interested in looking at the correlation structure.
It's like graphical lasso methods.
Yeah, so if you make an assumption about sparsity on the inverse covariance matrix, typically, you would use a graphical lasso or something like that to estimate the inverse covariance matrix. But it's an interesting question, like as you collect data from more and more brain regions. So in my field, we study at the level of single neurons, and we basically have this Moore's law-like effect where every 6 years or so, the size of the number of neurons we're able to record doubles. So the n is getting larger and larger. And if you think about it, the number of parameters you're estimating in your covariance matrix, your n by n covariance matrix, is scaling like n squared. And number of trials or samples we're able to collect is not really that scalable. So there's interesting results about how well you can estimate the covariance matrix if you make assumptions of it being low rank or approximately low rank, like the eigenvalues decay fast, and then also sparsity and things like this.
Your covariance would be like the correlation between the firing
Of two neurons, for example, yeah. And there's reasons neuroscientists care about this, because like if you imagine this is the firing rate of neuron 1, this is the firing rate of neuron 2, neuron 3, and let's say I have two different conditions that two different visual stimuli, cats and dogs or whatever, and I train my monkey to indicate whether it's a cat or dog. And this is the distribution of cats and dogs, or this is the mean of the two distributions in neural firing rate space. So obviously, I can separate these two, but the question is whether the noise on trial to trials is correlated like this, in which case it's harder to separate the two distributions, or is the noise kind of orthogonal to the stimulus coding dimensions? If it's like this, then I can draw a linear classifier and easily separate the two. So this is these noise correlations, what they're called, like between neurons, is something that a lot of people are interested in measuring, but it's really hard to do because you need a lot of trials. So yeah, this is one of the reasons I've been interested in applying tools from learning theory to see how well can you estimate these covariance matrices. Can you do better if you assume they're low rank? Can you do better if you assume they're sparse? And how much better do you do? Yeah.
So there was a talk yesterday about how to go back and forth from a low rank matrix to a sparse matrix.
Oh, that sounds interesting.
Yeah, it was very interesting. Like the technique was by solving this like sequence of constraint optimization problems.
Mhm.
I don't remember the name of the author, Lawrence something, Lawrence Sol.
Lawrence Saul. Yeah.
Oh,
Yeah, he's one of the people who did it was ISOMAP
yeah,
or locally linear embeddings, one of those two.
that guy, yeah,
Yeah.
was pretty interesting.
Yeah. Oh no.
But I didn't understand what you wanted.
Oh, I want this, I don't want it to be equal necessarily, but it's easy to see on a log plot, but this is actually decaying to zero faster than the orange. So what we're gonna show soon is that we're gonna have an even better bound that is tighter. So this is, yeah, the orange line is an upper bound. But in this particular case, there's additional structure in the way I simulated the data that we can make a better bound that is going to decay exponentially fast in n, whereas this is decaying like 1/n. So e to the negative n converges to zero much quicker. And yeah, is your question like why do we want to bound this, or like why do we want it to move to zero? Or...
I was just
Yeah, exactly.
Yeah, same.
Yeah, so yeah, but that's great. Yeah, so what you Googled is correct. So it's like this is less than or equal to something, and this orange line is that something. So yeah, this is just a simulation, just demonstrating that that's actually true. That makes sense. Yeah.
All this one.
Okay, it's 10:30. Let's get started again. How's the pace of this for everyone? Like generally, I'm seeing nods. Good. Okay. I think like what we'll do is we'll work through the rest of these slides. It'll probably take us an hour or so. Maybe to noon. And I'm going to skip the matrix factorization material because I'm having more fun with this than that. So as long as that's okay with everyone. Okay, so to summarize where we left off, we derived this Chebyshev bound on how well the sample mean estimates the true mean. And the bound is on the failure probability that we make an estimation error worse than some epsilon. And that failure probability decays like 1/n, so it eventually converges to 0. And it's true that if you don't make any further assumptions on x, this is actually the best you can do. However, you really have to try pretty hard to come up with adversarial distributions on x that saturate this bound. So in general, like the Chebyshev bound's really easy to derive, and it's, so if people still talk about it, it's like a good thing to introduce. But now we're going to do better, and we're going to use these Chernoff-Haupting bounds.
What do you mean we saturate the
I think I actually have it later. I'm going to skip through all this. This is just a preview. Okay, so I'm going to, just jump to the punchline, and then we'll go back and see how we get here. But we're going to derive this green bound, this Chernoff-Haupting bound, which you see decays much quicker than the orange upper bound, and also is upper bounding this true simulation I did in blue. And in general, so this simulation here was done where I sampled that x is from a Gaussian distribution with mean mu and variance sigma squared. And in that case, this Chernoff-Haupting bound will apply, but you can come up with these adversarial distributions over x where my ability to estimate the mean according to the sample mean violates this this Chernoff-Haupting bound. So in general, you see this is a distribution. I'm not writing it out because it's this really annoying distribution where you have 3 delta functions, one at 0 and one at like +n and one at -n, and they're weighted in a certain way. But if you come up with these kind of adversarial examples, the probability that you make an error actually only decays like 1/n, and that kind of saturates the Chebyshev rate of decay. So in many cases that are of interest to us, we can do better, and we're going to use these Chernoff bounds as a way to beat the Chebyshev upper bound. Does that make sense to everyone? Okay, so to derive these Chernoff-Haupting bounds, we're going to now assume, for simplicity, that the x's are Gaussian random variables. Now, this Chernoff bound is going to apply in other cases as well, but we're just going to take Gaussian random variables to walk through this. And again, we're going to assume each x has mean mu and variance sigma squared. And we're going to estimate, we're interested in estimating the mean. We're going to use the sample mean as a way to do that. And okay, so let's walk through how we're going to do this. So I'm going to define a new random variable zi, which is just xi minus mu. Now again, I don't know what mu is, but the assumption is that mu is a real number out in the world. So I only get to observe xi, but I can still define this thing mathematically and manipulate And the nice thing about doing this is now each zi is a zero need Gaussian random variable. It still has the same variance as before, but I've just centered it at 0. And now I'm not going to go through the calculation for how you derive this expectation for a Gaussian distribution, but it's not too hard. You use like the definition of the Gaussian density function. There's tricks involved with how you actually like do that integral, like if you're deriving this from first principles. But in practice, if you're doing applied research out in the world, like most of us, you go onto Wikipedia and you look up what is the moment generating function of the Gaussian distribution, and it tells you this is what it is. And I keep using, throwing around this word moment generating function. The moment generating function is just this. It's defined as an expectation of this exponential function where lambda is greater than 0. Okay, so for a mean-centered Gaussian random variable, just take this as a given that this expectation can be computed by doing some kind of annoying integral. Okay, so remember the idea behind the turnoff bound. The turnoff bound is just this. And the idea is z is any random variable, epsilon is anything that I'm choosing, epsilon greater than 0. I can multiply each side of this by lambda, take the exponential of both sides, and then apply Markov's inequality, because the exponential of that is a non-negative random variable. So this is, just really a direct application of Markov's inequality to the moment generating function of z. Okay, so this is the basis for the turnoff bound, and now what we want to do is plug in this expectation, as I mentioned to you before. So that goes into the numerator there, and then by properties of exponential function, take the division of two exponents is just the division turns into subtraction inside the exponential. Okay, mostly nods from the audience. Okay, now the cool thing about this turnoff bond is that this holds for any value of lambda greater than 0. So I think what I have you do on the next slide is to say, okay, this up here holds for any lambda greater than 0. This is just a copy of exactly what I wrote on the last page. Now what we're going to do is we're going to find the lowest upper bound implied by Chernoff. This is true for any lambda, so we might as well choose the lambda which gives us the best, which minimizes the right-hand side of this upper bound. So we're going to choose lambda star, which is the lambda greater than 0 that minimizes this. I gave you the answer here, but I think I also want to pause for a second and just have people think through how do you derive this. And once we give it a few seconds, if anybody can explain that, that would be good.
For the relative with respect to lambda and 0.
Exactly. So to minimize the right-hand side of this and the exponential, it's the same as minimizing, the argument to the exponential. And this is a quadratic function. It's a parabola. So I can take the derivative with respect to lambda, set it to 0, so you get lambda sigma squared minus epsilon equals 0. Add epsilon to each side, divide by sigma squared. That gives you the lambda that minimizes it. Okay, great. So now we have a value for lambda. What happens if we plug this value, lambda star, into this expression? Here you get epsilon squared over sigma squared. And here there's a lambda squared, so you get epsilon squared over sigma to the 4th, but the sigma squared in the numerator cancels. So use some simplification, and when all is said and done, what you see is that the probability of x minus mu being greater than epsilon, remember I defined this as zi in the previous slide, is less than this term here. Okay, so what's the next step then? Kind of been throwing some equations at you. So thus far, I've just derived this for a single x object, right? There's no n in this expression yet.
This is not that surprising.
No.
This is just the Gaussian evaluated that.
Yes, that's this is true. Now yeah, because it's mean centered. Yes, good point. It's missing the normalizing constant, but yeah. But the next step is to apply this not just to a single xi, but to the sample mean. So now we're going to think about bounding this probability here. So I'm going to start by multiplying both sides of that inequality by n. N is greater than 0, so I can do that. And now remember my definition of zi, which was just this random variable that is mean centered, because that's much nicer to think about. I guess that's the other trick, to go back to your comment about the tail probability, is like I subtracted off the mean in this way. So but yeah, so if I apply the Chernoff bound naively to this, I'm just going to get this bound here, right? So this is n epsilon is still a positive number, so I get n epsilon in the denominator. I have lambda in the numerator and denominator as before. So this is the simple statement of the Chernoff bound, which holds for any lambda greater than 0. Okay, so now this is the kind of crux of walking through this derivation. The thing that's really nice about Chernoff bounds or Chernoff-Hofting bounds is I'm assuming that my data samples or my centered data samples are IID and independent. And because of that, I have this sum inside this exponential. Well, so first of all, I can just turn by the nice properties of exponentials into a product. So that's one really nice thing about the Chernoff bound, is it has this exponential baked in. So that lets me turn the sum of things into a product of things. And because those things are independent, the product of random variables, or the expectation of a product of random variables, is equal to the product of their expectation. So I can push this expectation inside here because the zi's are independent random variables. So this is these two kind of things conspire in a really nice way to make Chernoff bounds very nice to this setting where we have IID random variables. And we can't do this as easily for even things like Chebyshev's inequality, because it doesn't have, like, an exponential doesn't appear anywhere in that result. Okay, so we've rearranged it to show that the probability of making an error is upper bounded by this product of expectations of this exponential function. Now, this thing inside here is exactly what we were just looking at a couple slides ago. It's the moment generating function of a zero mean Gaussian random variable. So if we plug in the expression for that, which is just x, so sigma squared 2, then we get that expression. Now, again, we have a product going from I equals 1 to n of a bunch of exponential functions. So due to the properties of exponentials, I can put this product inside the exponential to a sum, and all the terms are identical, so I just get n terms in there. So this n appears now in the numerator as well as in the denominator. It's going to be important. And yeah, this is just more properties of exponentials now, taking the numerator minus the denominator, and I'm factoring out a factor of n here. And now, again, we're going to play the same trick. Does anybody want to shout out what's coming next? Yeah, or minimize over lambda. Yeah. Yeah, so this bound is holding for any lambda. It's this parabola thing, and when we plug in, we just said on the last slide, the minimal value is given by epsilon divided by sigma squared. Plug that in and simplify. We get a negative n times this term. So now this is basically where we wanted to end up. So putting it all together, I mean, you can see it on this slide. We started with the probability that our sample mean is larger than, or the difference between our sample mean and the true mean is larger than epsilon, is upper bounded by this exponential function. You can repeat this argument for it being less than epsilon, and then together you just get a 2 out here if you wanted to bound the absolute value difference. So if you want an upper bound and a lower bound kind of on your, or that's not a bound, sorry, you want to bound the probability of having a positive error or a negative error. But the upshot of all of this is that, again, we've been proving these epsilon delta proofs, and we've been interested in the absolute value of our estimator's difference from the true mean. Chebyshev inequality, which we talked about first, says that for any variable, as long as it has finite variance, this failure probability, delta of n, is proportional to 1 over n. Now, the Chernoff-Hofing calculation that we just went through says that for Gaussian random variables, we can actually do much better, and this failure probability is decaying as e to the negative n. And in general, this bound holds not just for Gaussian random variables, but so-called random variables that are sub-Gaussian. So a sub-Gaussian random variable is just any variable whose moment generating function is upper bounded by a Gaussian random variable. Because that's really the only thing, if you look back at this proof, that we needed to make this work was that we plugged in this expectation, this moment generating function of a Gaussian has this really nice form. And if we want to generalize this beyond Gaussians, we just need that if Z is not a Gaussian variable, but it's something else that can be upper bounded by a Gaussian with a particular choice of sigma squared, then this still applies. And that's actually a pretty broad class of random variables, and people call them, again, sub-Gaussian random variables, with the intuition being that their tails are decaying faster than Gaussians, far out in the tails. Okay, so questions on where we ended up here with the Chernoff bound? Oh yeah.
So actually, sub-Gaussian random variables are like that's less realistic, because I would assume that in beta you have like sometimes outliers and stuff like this that are very far from the
Yeah. So here's the fact: any bounded random variable is sub-Gaussian. So in neural data, for example, something I work with a lot, what you measure are for each neuron, like you'll have a voltage recording and it gives electrical impulses. And due to biophysical constraints, there is like a maximal firing rate for how quickly this neuron can fire. So if we consider, a time bin of delta t, for example, then I want to think about what is like my probability distribution over x, where x is the number of spikes that this neuron records. And I know that it can't be less than 0, and it can't be less than some upper bound b, due to some biophysical constraints that somebody with domain knowledge could tell me. So there's some distribution. I mean, it's a discrete distribution, but I'll draw it as continuous. And anytime you can upper bound, or you have to lower bound and upper bound the distribution, this you can show is sub-Gaussian, because even if it's like uniform over this interval, the tails outside of this interval go to 0 exactly. So this actually applies pretty broadly. Like usually, it depends on your applications again, but there's a lot of situations where you can kind of say, okay, due to some physical constraint, there is some upper limit to what value I could actually see in this application.
So yeah, I guess in terms of modeling, you can also always say that you have a digital sensor that has a right. That's like
Yeah, exactly. Yeah, if you have some sensor that has an upper bound. I mean, now if you're measuring if you care about modeling the ground truth thing and not what comes out of your sensor, it may be different. But yeah, I'll try to think of something off the top of my head, but like some sort of electronic communications framework where I'm looking at the number of packets or something that have been transmitted over my network. There is some upper bound on like the bandwidth given by the bandwidth of my network. So anytime, you have bounded random variables, this applies. I'll give, I think, a couple other vague uses of this in a few slides that actually aren't even really statistical applications of these ideas, but you can apply these ideas like in more mathematical settings, like over random graphs, for example. If you have a random network or random graph with n nodes and they have some connection probability, then there's some probability distribution over the degree of each node, and that probability distribution is bounded, and therefore it's sub-Gaussian, and all this applies. Good question. Other high-level questions? So I showed this slide already, but this is just showing the same simulation I did, a few slides ago, and then I added this tighter bound, which is this turn on opting bound, and when you put the y-axis on a logarithmic scale, you can see that the Chebyshev bound, this 1/n decay, is much slower than this exponentially decreasing bound in green. And in fact, this Chernoff-Opting bound in this case tells me that once I go out to 25 samples, the probability that I misestimate the mean by more than the standard deviation is 1 in a million, and I didn't have enough laptop power to simulate that. So at a certain point, my simulation just dropped off. But it's a very, very nice result. That if you could, if you ever were in the world and you actually knew that there was like a Gaussian distribution that you were simulating from, this would be a really nice result, but it is a bit idealized, admittedly. Okay. And again, this goes back to a question earlier, does this bound always hold? And yeah, again, this is a different simulation with a different underlying distribution that wasn't Gaussian, just to show that the Chebyshev bound, unfortunately, is the best you can say in general without making further assumptions on the data. But if your variable is bounded, or your variable is Gaussian, or in general sub-Gaussian, then these like Chernoff bounds are going to apply and give you much tighter bounds. So again, I started this talk with an apology by saying we're going to be talking a lot about mean estimation, which is kind of maybe a boring problem. But I think it's, again, really a fundamental problem to really think through in detail, because it's a first step towards many more interesting and complicated problems. So we've talked about if you get n samples from an unknown distribution, how do you estimate the expected value of x? If you think about just a general regression model, linear or nonlinear regression, you can think of regression as being mean estimation, really, but you're doing estimation of the conditional mean. So the mean of, actually, sorry, it should be flipped, because typically you think of y as being the dependent variable, but whatever. You estimate the expected value of y given x. So it's still mean estimation, it's just it's a family of mean estimation problems parameterized by some independent variable that you're conditioning on. I have mentioned this problem of covariance estimation a few times, and this is one that I'm thinking about. It has applications in neuroscience, and there's many other applications where you're trying to do estimation of correlations or covariances in random variables. This is also measuring an expectation of this outer product. I mean, if x is mean-centered, or if you can estimate the mean, then really the tricky thing in covariance estimation boils down to being able to estimate with high confidence the expected value of this outer product, XX transpose. So it turns out that a lot of the tool, kind of standard results in how many samples of X do you need to estimate this, use things like Chernoff-Opting bounds in various kind of clever ways. But just intuitively, you can see that if you're talking about estimating the expectation of a random variable, there's many random variables that we're interested in, and these general tools can be brought to bear on that. I mentioned this idea of applying these tools not just in data science or statistical applications, but also just to prove results about in graph theory, for example. So if you have a random graph and you want to prove theorems about what is the probability that the whole graph is is connected if each node has a small probability, or you want to give a bound on what is the expected degree of each node. Like there's a famous result in graph theory which shows that if you have a densely connected graph, then the graph is very close to being regular, which is basically that every single node in the graph has a very similar degree. And the easy way to prove that is to use like a Hofting-Chernoff bound. And then, yeah, a final example comes from thinking about random walks on graphs, or the convergence of a Markov chain is kind of the equivalent way of stating the problem. So if you have a random walk of n steps on a graph that is connected, and you count the number of times that you visit node I, call that Ci, then a simple way to estimate the probability, if you run your chain infinitely long, the probability of occupying node I is just Ci divided by the length of your simulation. And that's, very similar to the various things that we've talked about, like coin flipping and stuff. And again, you can prove that this estimate of your stationary distribution of the random walk converges with a failure probability, and you can upper bound that failure probability using Chernoff bounds. So we've talked about really dead simple ideas, but these ideas are very generally applicable, and that's just kind of where I want to tie up this lecture. Okay, so we have one more kind of thing to walk through. I think it'll take, I don't know, maybe 10 or 15 minutes, maybe longer. I don't know, depends on how many questions and how engaged everyone is. But when we're done with this, that'll be kind of the end of the talk. So any questions on these broader ideas before I move on to talking about what I was supposed to talk about, which is statistical learning theory? Okay. So remember, at the beginning of the talk, we basically said, okay, we want to derive these error bounds to help us understand machine learning algorithms. And we've been talking about really dead simple machine learning algorithms, which are basically, predict the mean of a distribution. So let's talk about regression in the final kind of bit of this talk, just to give you a sense of how you can extend the Chernoff bounds and other bounds to these ideas. So we're going to observe data, and each data point is going to be, I'm going to jointly observe an X and a Y, and I'm going to try to predict Y from X. This is the classic kind of regression setting. Each X and Y draw is drawn IID from some unknown distribution, and I want to learn a prediction function, a regression function F, to predict Y from X. And then you're going to specify for me some loss function, and this loss function can, in general, be very broad. We're going to make some assumptions on this loss function, as you'll see, but for now, just think of this loss function as being squared error. So this is f of x is my prediction, y hat. I compare that to the true y, and I compute, squared error or some other loss function, and I want to minimize that. And specifically, what I want to do is not just minimize that for a single y, but I want to minimize the expectation of this loss over future samples from the distribution V of xy. So this is called the risk of a regression function. This is another kind of bit of jargon that you'll hear about, like empirical risk minimization and things like this. So we're going to be talking about risk minimization for this final example. The important thing to emphasize about the risk is that it's not something that you can actually evaluate. It's an expectation over future draws from the data. So given infinite data and future draws, I would be able to measure this. But obviously we don't have that infinite data. So we want to find the f that minimizes the true risk. So f star is the best regression function that minimizes the risk. But we can't draw infinite samples, so the best that we can do is approximate this expectation using something that looks kind of like the sample mean, but it's the mean of the mean loss over your training set, for example. So this is called the empirical risk of a function f. That makes sense. Like one of the slightly weird things here is the risk is a function that takes in another function kind of as its input. And we're going to be kind of thinking about doing this optimization over the class of all functions f, which is a little bit of a different thing than maybe you've like seen in the past, but it's I think it's pretty intuitive. So just stop me if I'm not making any sense. Okay, so what you typically do in a lot of machine learning algorithm is this empirical risk minimization. So you're going to say that f hat is my estimate of like the best regression function that I have. So R hat is the empirical risk, this average training loss. I'm going to train the parameters of my model by solving this minimization problem over the empirical risk. That learning procedure is going to give me a regression function f hat. And what we want to derive error bounds on is we want to say that f hat is close to the true, or there may not even be a true value of f, but we want to say that f hat is close to the optimal f star out of some epsilon. And remember how I defined f star on the previous slide is that f star is the function in my class of regression functions that minimizes the true risk, which I don't get to measure. So I don't get to measure the true risk, I don't get to measure f star, but I can measure r hat, which is the empirical risk, and I can get an f hat, which is the function that minimizes the empirical risk. Can I derive an error bound that says that the true risk of f hat is really close to the optimal risk of f star? And again, we're going to do this kind of epsilon delta formulation where we have some target level of accuracy and then think about bounding the probability of failure by some function delta then. Okay, questions on risk minimization and this whole setup? Okay, so there's a lot of things to kind of keep in your head here, but if you get lost at any point, just let me know. Okay. Oh, I didn't put in animation, so all the slides are just up here. That's fine. We'll walk through this one by one. So we're going to make two simplifying assumptions here that I think some of you in the audience might complain about. But we're going to simplify the proof, and they're actually not totally unreasonable. So the first assumption is that we're going to assume that our loss between y and our y hat, or predicted y of x, is lower bounded by 0. I mean, that's pretty easy and generalizable. We're also going to assume that it's upper bounded by some number, and then we can always rescale by adding a constant and multiplying by an appropriate positive number, so that the loss is bounded between 0 and 1. That's just going to be convenient for us. Now, if the loss was a quadratic loss, that's kind of in theory unbounded. It can be very high. As the error goes up, the quadratic things are, obviously going to infinity. So what's typically done, I mean, there's many ways to think about this in the case of linear regression, for example, is that you put like a bound constraint on your regression coefficients. So if y hat is equal to wx, where w is a matrix of regression coefficients, then you could just say, okay, my regression coefficients have to be bounded between -100 and 100, for example. So if I put a bound on how big my regression constraints can be, if I use things like ridge regularization, for example, that's going to bound f of x. And then, yeah, the other assumption that goes with that is that x and y are also bounded within some range. So if everything is, somewhat bounded, even in the case of linear regression, you can think of reducing it to something like this. Yes.
Isn't it simpler just to say we're using a computer and the computer has a finite number of movements of precision, and therefore it's always bounded no matter what we do?
Well, that's going to be the second, that's going to relate to the second assumption, which is that the set of regression functions has some precision.
Well, the loss that you calculate will always be bounded, as well as the functions you can calculate.
Well, I mean,
No, I'm agreeing with your assumption.
yes, yeah. Yeah, no, I mean, so, yeah, I don't know if that gets you out of the boundedness problem, because, I mean, there is this like special symbol for inf, right, or kind of overflow errors. So yeah. Yeah, that is potentially. I don't know. I don't know if I want to endorse it or not, but it's an interesting way of thinking about this. And it relates to the second assumption we're going to make, which is that in linear regression, there's like an infinite number of possible models, or our hypothesis set is infinite because there's an infinite number of regression coefficients and matrices. For our proof, we're going to assume that there's a finite set of regression functions that we're going to minimize over. And that seems like a strong assumption, but again, on computers, for example, there's only so much precision that you have. So you can imagine basically putting a constraint on your regression coefficients that, okay, I only have 6 significant digits or something. And then everything is discretized, and this actually is, a finite set of functions. And what's really surprising is that that kind of trick, it seems really like quick and dirty and unnatural. It actually gives you like a pretty reasonable way of deriving the correct sample complexity of things. You get like these horribly huge constants or whatever, but it gets you the right scaling behavior of like x to the -n or whatever. So it's actually endorsed by the textbooks I've read, at least, as like a pretty quick and dirty way. It maybe doesn't always give you the right answer, but this is a quick way to, when you're first working on a problem, derive some upper bound. And then if you're happy with the result, you can kind of roll up your sleeves and do something a little bit more sophisticated over the set of infinite hypothesis classes. The other thing I want to point out is for the bounding the loss between 0 and 1, like another really simple setting where this applies is classification. So if you don't think of regression in terms of predicting a continuous variable y from x, but I have, let's say, x1 and x2, and for each data point I have circles and crosses, and all of these up here correspond to y equals 1, and these down here correspond to y equals -1, for example. And I have some decision boundary, which is a function of my x's, and this decision boundary makes a prediction. A simple loss to use here is just equal to 1 if you're correct, and equal to 0 equal to 1 if you make a prediction. Let's say my function predicts a circle here on this side, but in reality it was across, that would be a loss of 1. And if the function makes a correct prediction, the loss is equal to 0. So might as well just write that out, because I think by saying it out loud, I probably confused everything. So this loss function is equal to 0 if the sine of y equals the sine of f of x, and it's equal to 1 otherwise if the sine of y is not equal to the sine of f of x. So if I just want to think about classification, binary classification or multi-class classification, these kind of bounded loss functions show up. So this isn't like a totally unreasonable and limiting assumption. Questions on that? Okay, so next thing is we're going to use the Chernoff-Hofting bounds. And our goal is going to be to bound our first goal, which is going to be a step towards the final group, is that we're going to say for each function in our finite set of candidate functions or candidate regression functions, the empirical risk is going to concentrate close to the true risk. So that the probability of my empirical risk being more than epsilon worse than the true risk is going to decrease exponentially with n. So this is an application of a Chernoff-Hofting bound that we've seen before. Yes, question?
Like there should be some constant here that we don't times the exponent.
Times the exponent?
Right? Because
I think the constant is 1.
because if
Or
the loss
there's a divided by L squared here.
like because the loss is the maximum of the loss is 1.
It's because the maximum of the loss is 1. If the maximum was L, there would be a divided by L squared inside the exponential, which you can think of as a constant up front. Yeah, this is, I don't think there's a constant here because this is, because of various simplifying assumptions. I think I derived this. Do I derive this? No, I don't, sorry. Yeah, this is actually the classic Hofting bound.
Okay.
Yeah.
The variance is bounded by the maximum value.
Yeah, I think.
Value squared, so that's why L squared.
Yeah, I think that's yeah, exactly.
So what is an example for a finite hypothesis curve?
Yeah, so let's think about the linear classification example here. So it's a bit of an artificial assumption, but it makes the proof very easy. But the idea is, let's say I'm doing linear classification between something like this. My hypothesis class is going to be some finite set of, sorry, I was trying to draw this, it's like a pinwheel. Let's say I put down a grid of points, and then I have a, set of equally spaced like 10 lines or something like this. And then I draw down a grid for different centers for those lines. Then I can do like a brute force search over all lines and find which one of them minimizes the loss for linearly separating these two classes. That's a kind of simple example. And another example, again, is like if you run something on your computer, there is some finite precision to, like, your computer can't represent all infinitely many hyperplanes here. So at the end of the day, everything is actually discrete, but it's just the number of functions in your hypothesis class can be really, really, really large. So that's like the one aspect of this proof that's going to be a little bit artificial. And various things that we're not going to talk about today, when you extend these ideas a little bit more elegantly to machine learning algorithms, deal with, like, what is the right way to quantify how complex and large this hypothesis class here. So if you've heard of the, like, VC dimension of a class of regression functions, that's in some sense a measure of how big or complex the class of classification of regression functions is. The Rademacher complexity is another notion of complexity, things like this.
But at what point comes the size of the hypothesis class into play?
Yeah, we're going to see it on the next slide, I think, right away, actually. So the first step is kind of applying this Chernoff-Hofstadter bound to each F, each candidate regression function, each one of those possible lines I drew. So the Chernoff-Hofstadter bound applies to any F. The true risk of F and the empirical or estimated risk is within epsilon with exponentially high probability. And now we're going to basically do the union bound over all of F. So what we're looking at here is, now instead of looking at just a single probability of making an error, I'm going to look at the worst case error. So I'm going to look at the F which maximizes the difference between its empirical risk and its true risk. So maximizing over, like, this is the worst case loss over all candidate regression functions in my class in my hypothesis functions. And the probability that I make an error greater than epsilon over 2, you'll see why I divided by 2 in a second, is upper bounded by the union bound, which is just to say, I'm going to take this probability for every single F in my class and multiply by the number of times this happens. So the worst case loss, the probability of my worst case risk misestimation being bad is upper bounded by me making an error on any one of the F's times the total number of F's.
So that means for, like, a very simple linear regression, it's basically infinite.
Yes, so if it's basically infinite, but because F is finite, it's not quite infinite.
Yeah, okay. But
yeah. So the thing that's weird about this proof is that, like, we're going to kind of, this is a very, very large number, but it's still going to give us the right dependence on n. And what's interesting is that if you, like, work through a more rigorous mathematical proof of this idea, and you think about bounding or measuring the complexity of the class of all linear functions. So for classification, the kind of right way to do that is through the VC dimension, which is actually, like, pretty simple. For linear regression, it's more difficult. There's something called the pseudo dimension, which generalizes the VC dimension to linear regression. So again, like, doing this in the infinite dimensional, or sorry, not infinite dimensional, doing it in the case of having an infinite set of prediction functions is trickier and beyond the scope of what I'll talk about, but yeah, nevertheless, let's just go with this for now. Now I'm going to apply the bound on the previous page where the previous slide is just the true not bound here of -2. And because it's epsilon over 2, the 2 cancels. So I get this exponentially decreasing probability of failure. So what we've shown is that, okay, so with high probability, the estimated risk is close to the true risk for every F. And now we're basically done. Because, so I'll walk through this a little bit slowly. So we start with the true risk of F hat and the true risk of F star. Remember how we defined F hat and F star. So F star is actually the thing that minimizes R of F, the true risk. F hat is the F that minimizes R hat, which is the empirical risk over the training data. And what we want to show is that this thing here is less than epsilon at the end of the day. Because that is what we originally wrote. The risk is the overall thing we're trying to minimize, and if this whole thing is less than epsilon, then we're within epsilon of the optimal solution. Now what this up here tells me is that for any F hat or F star included, I can replace R with R hat and add epsilon over 2 without changing the probability. So if this holds over all F, then this will hold when I add an epsilon over 2 and I switch the R's to R hats. Is that clear? Because up here I'm showing that the worst case F is going to be less than or equal to epsilon over 2 here. So let's say like the worst case scenario for us would be if F hat was one of the functions where the empirical risk was a really bad estimate of the true risk. So in this case, F hat would be the one here, but we're still with very high probability saying that it's within epsilon over 2. So at the end of the day, what happens is we're trying to bound the true risk of our estimated F versus the optimal F star, which we don't know. We change the R's to R hats, and we have to add this epsilon over 2. And with high probability, this is an upper bound. And then all we do is combine the epsilons over 2. And now remember that F of hat is the F that minimizes R of hat. So this whole thing, this is lower than this. So this is less than 0. So this whole thing is less than epsilon. So there's quite a few steps that you have to kind of walk through there. Hope I was able to walk you through them to some extent. I think that's the last slide. Whoops. Any questions on that final slide as I bring it back up? Great. So the summary, just to bring you back, summary of what we just proved is exactly this, that you get an estimated function f of hat, and its true performance is within a small value epsilon of the optimal performance that we could have achieved within our hypothesis class. And that occurs with exponentially small probability of failure. So happy to give people references for those proofs if you want to chew on that a bit and look at how to extend it to even more practical real world cases. But other than that, I think that's all the content I have. So I'll just take questions. Yeah.
Can you go to last slide?
Yeah. Oh, shoot, I hate that. All right.
Here, in the end, didn't you need to, instead of maximizing the above probability for any f, didn't you need to do it for any two f's, like for two different, like
Yeah, let me state it this way. So what I want to bound is that the probability that there exists an f within my hypothesis class for which I make a really bad error, a bad estimation of the risk that's greater than epsilon over 2. So through the union bound and then through a Chernoff bound, what you can show here is that with high probability, there does not exist such a function that I make a really bad estimate of the true risk. There's not a single function in curly f for which the empirical risk is epsilon over 2 greater than the true risk of that function f. With this exponentially, so as long as n is kind of sufficiently large, or as n increases, the probability that I'm making this kind of error is decreasing exponentially. That's what this first part says. So this applies to any f. So it applies both to f hat and to f star. So both of these, the true risk is well estimated by the empirical risk. And what I did in this inequality is I just substituted the true risk for the empirical risk, and then I have to add this epsilon over 2 accuracy term. The epsilon over 2 is how well does r hat estimate the true risk. So I switch from the r hat here, and I get 2 epsilon over 2 terms. I add them together to get epsilon. And then the last step is to look at this r hat of f minus r hat of f star, and notice that this has to be less than or equal to 0 because I defined f hat as the function that minimizes the empirical risk, which is r hat. So at worst, f star is equal to f hat, and this is equal to 0. In other cases, the best regression function is something different, but it can't be better on r hat. Yeah, thanks for giving me a second chance walking through that. It's kind of it's my first time going through these slides, so this was really fun, and I appreciate all of you for your attention and questions. Okay, so it's 11:30. I'll take more. I'm free for questions if there are any, but otherwise, I think we'll stop.
All right, let's get started. The first 25-ish minutes is just about the intersection of ML and physics. This is based on a NERP tutorial I gave in 2021, which was 4 hours long. So I'm not going to go through everything, just going to select bits and pieces of it. And then we have a coding session, which likely lasts more than 20 minutes, unless you already have run a bunch of network without issues before. And I'll talk about sort of generative models in physics with deep learning. A lot of people do it very intensely. I was talking to people in DeepMind, and they were like, we really want to accelerate simulations. And I was like, why? As for physics, it makes sense because we want it to be a theoretical prediction of what will happen in the real world. For DeepMind, it's interesting because for them, the simulation is the way to generate more data set to train the neural network. And usually they just can't find that much data. So simulation data is actually more important than you think. And they want accelerated simulations because think about all the stuff they do for reinforcement learning. They need to do it very, very quickly and lots of loops. So because of that, accelerated simulations is actually a big topic and a major actually venture in the DeepMind. That's why we work a lot with them. So intersections of ML and physics. Okay, so on the left-hand side, I would sort of split it into two sides. The left-hand side is ML for physics, like what machine learning has done for physics or science. You can read it either way, it's really. It's just I'm more familiar with the physics world. And physics for ML. So there are two sides. In the past, for ML for physics, it's mostly used for fitting pre-existing models to data or discovering strong signals, like really like 5-signal signals, stuff like that. But present plus future, we have a bunch of generative models like accelerating simulations using ML when we know almost or all of the relevant physics, using ML to assist in scientific discovery, experiment designs, representation of the data, data cleaning, and inference. So all this stuff that you probably heard a little bit over the course of last week and a half. Miles probably did he talk about scientific discovery in terms of using like PyStar? Yes, a little bit. Yeah, so I gave a whole talk on scientific discovery earlier today on using ML with combining the neural network and PyStar. We can talk more about it if we need, but I suspect Miles covered it quite well. And also using ML to obtain models that are physically understandable. So that kind of goes into the area of interpretable ML. And that's something people are super excited about because A, they want to understand the network. For scientists, we might want to understand data that the network understood, but we have not figured out the theory. So that's what we got super excited about. Physics for ML, there's a lot of physicists actually who went and do ML right now. If you talk to the people who have done it, I just realized I could have just taken off my mask because you guys are way far away. They have physics, information theory, and statistics are intimately related in the goal to extract valid information from noisy data. So this has been always happening. It's not now, it's just been like that. If you look at information theory, you realize that it's actually related to statistical theory, related to all these like information theory bottleneck stuff. That's all connected. You learn physics and statistics and computer science, you realize they are very similar people actually contribute to the same area. Present plus future, a lot of us have started looking into this. For people interested, you should look up, actually we'll talk about Lagrange neural network today, which you use conserved quantities or symmetries or structures of the physical systems to provide inductive biases to build model better. I mean, architecture model, right? So we have done that ourselves here, and people have started doing that in terms of imparting symmetry, very strong constraint models. When you use graph neural network, you have a very strongly constrained system, right? So you can't just, it's not like convolution neural network when you do a graph neural network. You actually only see the local system. You don't see like it's a grid and you know exactly where the positions are, like on a grid. So have to start thinking about, actually, this is a good question. People, how do you compare convolution neural net and graph neural network? Because you guys have seen a bunch of these different things over the semester, over the 2 weeks. Suggestions? Don't be shy.
What do you mean by compare?
How, is there other things that you have to use graph neural network, and is there things that you have to use ConvNet but not graph network, and the other way around? For example, that's one way to compare it. The other way to compare it is, are there symmetries that you think exist in one versus the other? That's probably an easier way to think about it. What are the ease in terms of the engineering know-hows, right? So when you run graph neural network, you have to do RBF, these like encoding stuff, but then it's a different encoding when you do convolution neural net. So Anything you guys want to suggest? Raise your hands. Yes, please.
I guess convolutional neural network is a subset of a fully connected graph neural network.
And the graph network people would,
Well,
was
Not a fully connected, a grid graph. Well, it's that's why it's a subset.
So the GraphNet people would say that, and then ConvNet people would say that you cannot do everything ConvNet can do with GraphNet. And they will probably give you very good examples.
Okay.
Because when you do graph network, for example, unless you explicitly code it in the positions of where everything is into the nodes, you lose the information of where things are in the ConvNet where you're on the grid. You can code it up specifically, and then the question is, can you do sort of multiple message passing to get to the multi-scale physics that you could have gone in ConvNet? But yeah, so more questions. These are like research questions people are asking. So I'm not expecting you to know all the answer, but just want to, for those who have been thinking about this, to inspire you to start thinking.
GNNs tend to be.
Can you speak louder?
Sorry, GNNs tend to have equivariance with respect to node order. So
permutation symmetry.
Yes. Yeah.
That's right. And ConvNet does not.
Does not.
Yeah, but a convolutional net has translational symmetry usually. So you put a cat here, it's still a cat over here. Still recognize the same cat. Other suggestions? No, nothing. So there's a lot of people trying to figure out how much locality, is related to this discussion. So convolutional neural net has less constraint on being local. So GraphNet is always like the local node is connected to. While ConvNet does not, because it's just a grid and you're doing, filters on these blocks basically. So that's another way to think about what problems work better with convolutional neural network, what problems work better with GraphNet. Actually, any suggestions?
Why is it not local? I mean, fundamentally in your filter, you're also just considering your local neighborhood on the grid, right?
It is true, but you can have multiple layers to do it. And you'll argue, well, GraphNet can also do multiple message passing. Yeah. So then the question is, do you have the positions encoded in the GraphNet so you know exactly where the local info, are you conserving all the local information? So, but this is a good question. I mean, I thought about the same way, can I just do multiple message passing and just keep doing all of it?
What's the difference between the edges in a GNN and the positions in a CNN? Or the grid in the CNN?
Well, so I think the GraphNet people will think, I'm just going to be the GraphNet advocate for 2 seconds. I should do a lot more GraphNet than ConvNet myself. The GraphNet people would suggest that the GraphNet, the edges can describe interactions, and so there's a causation that you can encode and stuff like that. Well, ConvNet doesn't necessarily have that. So I was thinking during the beginning of COVID, I started looking at GraphNet myself, and then I started modeling, transmissions of people, people movement and the COVID rates in each city. So the COVID rate in each city are in the nodes of the graph, while the movement of the people can be described by the edges. And then, you can vary a bunch of things and see where it fits data. Turns out the data is so noisy at the beginning of pandemic, everything fits. But ConvNet will be very hard in principle to do that particular architecture, right? To do that particular data structure, I should say. So people will say, well, there's something that ConvNet doesn't do that the GraphNet would do, for example. More suggestions. I know we should have a lot of discussion later. This is good. Other people. Yes.
I guess it's easier.
Can you speak up? Sorry.
Yeah, I guess it's easier to encode data with the ConvNet or to a lower dimension than a graph neural network, although I don't really know much about GNNs. So,
did you guys run any GNNs at all throughout the class? Ooh, okay. I have not had a GraphNet one here, but I have two collab notebooks, but it's not mine. I just find the ones I know works online. That we can point out more notebooks later. Maybe we should just share to the group about GraphNet. We have ourselves, our group has a bunch, so we can definitely share with those guys. On the other hand, many people are not using Graph Network. Have you noticed? People are still using mostly convolutional neural network for most things because NVIDIA, FAIR, all these places are looking at images that are very complex that doesn't necessarily have these node edge attributes. So, all right. I know this is a huge digression. I'm just talking about conserved quantity symmetries and structures of physical systems. Provides inductive biases for model building. Model here being architecture building. So when you build model, you should start thinking about what are you trying to do that makes it different from the other model, right? And that's why I was trying to inspire the discussion about ConvNet and GraphNet. And there are multiple GraphNets. There's message passing GraphNet, there's graph convolution neural net at the minimum. And people who do either one of them will tell you the other one is worse or better, depending on who you talk to. So yeah. All right. And then, all right, physics for ML. That's the other part is that you can provide very complex data sets where question, go ahead.
Wait, I had a question. So like CNNs have like they take into account like local information.
Say that again. I can't hear you.
CNNs take into account local information, but transformers also do something similar by where they look at like neighboring or like the whole like input. So do people like how do those compare?
It's great. Actually, we just had a paper accepted using transformers to do. We just have a paper accepted using transformers to do simulation acceleration. We used to do convolution neural net, basically UNet that you guys will run later on today. But then we realized transformers allow you to do something like, if you have a next word you need to predict, you actually need to look at the whole sentence and then the whole sentence, even the whole paragraph or the whole chapter, right? So these multi-scale physics dependence that exist naturally in transformers don't necessarily exist in convolution neural nets. You have to sort of work it in, and it actually works out much better. It turns out using transformers for these turbulence simulation data set that we have benchmark. So we had a paper in Clear that actually beat all the benchmark using for turbulence simulation acceleration using dilated residual neural network. But then we used transformers and it has better performance. So transformers may be the way to go, who knows? But this is very early. We're still working on a bunch of different data sets to make sure it's not just for that one set of data.
Okay.
That's a great question. So transformer is another, thing you should say, okay, why don't we just, everything is about transformer. If you're on Twitter and you watch all these trends for a while, you realize that for a while, it's like attention is all you need. And the next thing is like, I don't know, transformer is all you need. And then next thing is now it's like DALL-E 2 diffusion model is all you need, right? So it's always one after another. Do people know what DALL-E 2 or DALL-E is or Imogen? Actually, take 2 minutes on Twitter. It's fun. Just take 2 minutes, Twitter on just hashtag DALL-E 2 or Imogen. It's fun.
How do you spell that?
DALLE 2, like DALL-E, like the artist, but now it's made by a machine. It's using
like Wall-E, right?
like Wall-E, yeah.
Like Wall-E, but with a D. Exactly. So DA.
So if you do 2, then it's the new version that came out from OpenAI. Imogen is the other one from, I forgot which company.
Google.
Yeah.
It's from Google.
It's from Google, yes. You don't have to be so loyal to them. My husband works for Google, so I was like, yeah, it's good this stock is gone. Or Imogen, which is another one. And that's another trend that's based on diffusion model these days. And then people will say, well, diffusion model is all you need. So it keeps going. And I think just be critical about things when you say people, oh, this is all you need. Yeah, diffusion models takes forever to train. Just for those who haven't tried. I tried for one of the older models. I'm not sure about DALL-E 2 because I don't have access to it. But diffusion model, the old one, like the first one was like 2016, I think. That one took forever. someone find like a cool image that's not terrible I want to share? I like the sloth playing the guitar one.
Oh,
I
I
don't know.
saw that one today. It's like,
Yeah, it's cool. Yes.
Do you see any value of these for science?
This is a great question. One of my postdoc and collaborator, Kay Swan, was saying the other day that like tell me one reason why I want to do the diffusion model, right? A is slow, which is true. B is like you just generate crazy stuff that doesn't really do anything. For science, I don't know yet. We wanted to try using diffusion model for simulation acceleration and see what is faster. But if it does take 10 hours to train, then it's not really accelerating that much. So why don't I just use the other method? For creative arts, that's what people claiming DALL-E 2 and imager models are for. I don't know, people have any suggestions after seeing all these images online?
I heard someone saying that they thought it would be useful for generating images, like for giving talks or something. If you want, like, you spend all this time like photoshopping things together for your talk. If you could just tell DALL-E to make it.
That would be cool. One of my friends have access to both Imager and DALL-E 2, and I think he hasn't used it for generating slides yet.
You should try.
Should try. Any cool ones you guys want to share? You guys, I asked you to go on Twitter and no one shared anything. Nothing? Nothing fun so far in DALL-E 2. Did you see the Minimals with Darth Vader? Okay. So a lot of artists actually are super excited about this. So I don't know if you know about the recent sale of pictures, not recent, a couple years ago sale of pictures, where they fetched, I don't know, several $100,000 for a picture that's generated by AI. They just framed it nicely. I thought I should have done it, but now people are actually probably going to do, you can just sell DALL-E 2 pictures because you can just type whatever you want. It shows up of a choice and frame it. Okay, but I don't know a good scientific one yet because if it's slow, I think it's going to be hard to do it for acceleration or simulation. But the first thing I thought is a simulation acceleration because it's like a cool generative model that you can control. I mean, somewhat this whatever you want to do with it, right? All right. Okay. Continuing translation of ideas from physics to ML. That's cool too. All right. So let's start with some examples. We're going on the ML for physics side, just to give you guys a sense what's been happening. These are like really old work. This is like old machine learning. People have been doing it for like SVN and KNN. People still use it in astrophysics. I'm sure in other sciences too. The other day, I think actually just across the street, David Hawk just talked about this paper that's really awesome. When they say dimensional reduction, they really just mean PCA, and it actually works beautifully. So don't we disregard all these other models that were old. They work really well. This is an old paper that we did before deep learning is all the rage. And we actually started doing the same thing now with graph neural network. It's better, yes, but is it infinitely better? No. So it's a good thing, something to think about what to do, right? And then this is another work that we published in ICML. Simon Raffenbach is actually a professor now at Miller and University of Montreal. And he at that time was a postdoc with us, and we asked him the question, okay, we have these cubes of universe that look completely identical to each other, but they are fundamentally very different. And these fundamental constants, oops, sorry, I don't know what that is doing. I need to have a stick because I'm very short. Oh, actually it's okay. I will just show it here. These cubes are very, very similar. I don't know if you guys have seen all these like mammograms pictures where they all look the same, but then somehow the machine was able to tell this person will have breast cancer 3 years down the line instead of what the technicians can tell you or the doctor can tell you. So 3 years down the line before the doctors can tell. So, there are things that the machine was picking up, but we cannot. And even specialized humans cannot. In this case was the doctors, in this case might be the cosmologists, right? So what we did is that we used our normal method, which is this power spectrum analysis. Mind you, at that time I was still pretending to be a cosmologist. So I do this power spectrum analysis, which basically means the traditional method of analyzing this data set. You take a Fourier transform of this cube and also the real data of the universe, which is much more complex, and then try to figure out what the true fundamental parameter of the universe are. What happened in the initial condition of the universe. So that's what I do. That's how I got tenure actually at CMU. And then we say, okay, how about use convolution neural net? This paper was in ICML because there doesn't exist a 3D convnet at that time. We wrote one and that was accepted. Much easier than now, turns out. And the method was a lot better. You see the blue crosses was much better than the red dots, which is the method that everyone uses at that time. Still do actually at some level. I would say half-half. People would run the red methods now, and then we do something called simulation-based inference ourselves to do a different method. People still do convolution neural nets, but people don't trust it yet. And that will come to the interpretability problem that we'll touch on later in class. Like people don't trust if you run a convnet and give you a number. They just don't trust you. So there's a trust issue from the science side. But it's also, we don't have good error bar. Bayesian neural network is not as well developed as I think we hope it will be. That's another area that could be of interest for those who are thinking about the cross intersection ML cross science, that the methods that has been developed are not actually that good yet. So there's no method that actually are producing the correct posterior for things that we know exactly what the error bar should be. Like take a Gaussian data set, you know exactly what the error should be. And all these methods that's produced by machine learners in BNN do not produce them, especially a high dimensional space. So there is an area I think that will be interesting to look at. And this was just done convolution neural net 3D, right? So that's something you guys probably, hopefully would have done or will do later on. Present plus future. All right, this is another paper. I don't know if you guys heard of Fourier neural operator. This is a paper where they want to accelerate turbulence simulations. It's led by the director of NVIDIA AI group, and Anima Anakumar. So her group has this 4 or 3 papers all about the same thing, which is accelerating turbulence simulations with different methods. And the different methods tend to be like transform the data with different bases. This one is Fourier basis. They basically Fourier transform it, UNet, inverse Fourier transform. And this is like splash in Nature, and it was interviewed and everything. I would not talk about the performance of the stuff when I'm recorded, but we'll talk later about that. And then the other thing is that there are other bases that you can interact with the data and then combine with the current architecture and see how you can improve things. So they just improved from UNet to basically Fourier transform and inverse Fourier transform. Combine it together and supposedly do a lot better. That's one paper. This is the paper we actually work with Kimberly Stechenfield. At that time, it was still a NERF's workshop. Now it's accepted in ICLAIR 2022. Kimberly Stechenfield is DeepMind research scientist. We work together on this paper. And what we do is that we use a very simple residual neural network. And it's called dilated residual neural network. It's a very simple extension of that. And it beats all the benchmark in turbulence acceleration, simulation acceleration, even the Fourier neural operator we just talked about earlier. So you don't need all the fancy stuff like the basis, but you can still do really well with very simple convolution-based neural network. So that's another question for you is that, are these symmetries helping sometimes? Because this one doesn't have any symmetry, except translational because it's convolution, neural network based. So, but this one beats it. So. This is showing you the ground truth on top, the predicted role in the middle. And I'll show you one more thing later. This is a cool question to ask. When we add noise to the training data and the weights, they perform better. The network perform better. Anyone has any ideas why?
During training, there's some uncertainty in because you're kind of discretizing it to a grid.
You have to be louder. I went to lots of punk concert when I was younger, so I cannot hear anything.
Sorry, I was saying there is some uncertainty, right? Like in the input data itself, like because you're doing like grid level, like there are some effects due to like this discretization and so on, like so to capture like all of those uncertainties.
So That's something I haven't thought about, but that is a good point. There is uncertainty in the generated training sets, right? So because we have to grid it, we actually don't know the answer to this question. It's an active research area. Rex Welling recently just talked about it too. He also observed it in his work. We observed it in our work too. I'm working with the Center for Data Science Director in NYU, Julia Campe, and her students also working on this, trying to figure out why just adding Gaussian noise works better by quite a lot. We're talking about things when you projected row out here. Actually, I'm going to play this again. I mean, we show you the good parts, but once it's like 160 steps down the line, before that, it actually even blows out without the noise. I actually can probably show you guys later when we're doing the coding session for the blowout version. And then if you add the noise, it actually rolls out a lot better.
Is that during training or
During
test
training.
time? So isn't that just because it's pushing the mean towards 0 maybe?
I don't know. I don't
Mean
know.
of the output.
This is a good question. We only added Gaussian noise, right? And this is not just us. The DeepMind folks like Kimberly and others also added noise to the training set. And it's also true for graph network, not just convolution neural network based. So the graph network data that we try to do where we model the planets moving also needed the noise. Once we forgot to turn on the noise flag, everything failed. And we're like, what happened? Yes.
So this CNN, it's trained on like one-step manner, or do you?
One-step training. Good question.
So then, like the errors kind of get propagated like across time, right? So like the noise kind of helps you. So at training time, you're only exposing it to one step, but at test time, you're actually rolling out like full. So the errors that get accumulated every step, like the model has never seen its own errors in some sense.
Mm-hmm. So that's my suggestion to these students to look at, which is basically once you do a one step, right, then you're creating noisy stuff and then you roll it into the input of that one same network. So I would expect the distribution of the noise of the output of this one step will be similar to be the optimal noise that you want to put in for the training. But so far, that's not what they see. So I might be right. That's my conjecture as the first one.
Does it help with the training dynamics? Like it just makes things more stochastic and maybe helps you explore better?
There's also possibility like a stochasticity of, because these are very chaotic in stochastic systems. Maybe that was why, because you just want to see more variety of situations. That's another possibility. But right now, my conjecture so far failed. And they're trying to find adversarial noise, that is making this better. So like that's not just Gaussian noise, because right now it's just white noise, right? Okay, so these are interesting directions to think about. Again, these are open research problems. I'm not asking you guys a question I know the answer to sometimes. Not all the time. Sometimes I don't. But that's why it's cool to do, machine learning or deep learning, because there's so many open problems. I think that's especially cool in cross science because there's so much people haven't touched on. Like there's a ton of people who've done ImageNet, but not that many people know about turbulent simulation because it's hard. Here's what we did actually using, we did it, but Nick, Peter Battaglia and his group at DeepMind have created these interaction network, which is message passing neural network, which is a type of graph neural network. They will tell you that this is the best one. I like them a lot because we work together and we can actually do the truth and the model fairly well as this one-step rollout that we just talked about earlier, but using graph network architecture. And this is things that you can accelerate simulations a lot using ML because the truth and the model basically look the same. Again, this is the pretty version. After like 3,000 steps, it will stop. Work looking well. And for very chaotic systems, this is harder. Yes, question.
I just wanted to.
You guys both raise your hands. I don't know. You guys have to fight off each other. Face off.
Go ahead. Go on. No, go ahead. Okay. Maybe just to throw it into the room regarding the noise. So in chemistry, there's
Can you just speak up? Sorry.
Yes. So in molecular dynamics, there's a very similar procedure called rattling. So you kind of have molecular dynamics trajectories, and you also just add in Gaussian noise to these molecular configurations. But there it's because like when you simulate dynamics and take like snapshots from that, you're very close to an equilibrium position. And the rattling just kind of gets the system into configurations that are a little higher in energy. And so the machine learning model sees more variety.
So similar to what he suggested was stochasticity, so
I-
that
I
increase
guess so, yeah.
stochasticity in the system that you're putting data in. And then I guess the question to test this is to take the data set, and then just add noise to the data set instead of, well, adding noise like data augmentation wise, right? So increase the training set, increase the amount of training set and add noise that way instead of adding noise along the way.
Yeah,
So and see whether it gives the same answer. If it doesn't, then it tells you something else is happening.
Mhm.
So that's one test. I mean, if you guys are interested, there's so much to do. So, other questions? Yes.
My question was just regarding the acceleration. What kind of what are you expecting or what are you seeing? What kind of acceleration ratios or how much time is saved? Or
One of our work that's actually was way back, like back in the days, we accelerated simulation by a factor of 1 million times of the universe. We simulate a universe and usually it would take X amount of hours, then it's like a millisecond using them. So there is a significant.
So, for example, for what I'm mostly interested in would be for turbulent flow simulations.
Say that again, I can't hear you.
For turbulent flow simulations, what kind of accelerations?
Those speed up actually, the one I show you doesn't speed up too much. Like we're talking about factor 10 to 20 because we're running very low resolution simulations. So the turbulent simulations here that we actually want to work on is something called the closure problems. I don't know if people, I mean, some of you know closure problems really well. Not all of you, but we wanted to figure out whether we can find these terms, these extra terms that only exist after you run the high resolution simulations. And you don't want to always run the high resolution simulation to get them. So like, how would you do it? So we try to use ML to help. And that's why we didn't concentrate on accelerating simulations. But in principle, the Fourier neural network operator that we talked about, NVIDIA just had the GTC conference a couple months ago, and it showed that they created twin Earth using the Fourier neural operator, which basically means they model the ocean turbulence with this Fourier neural operator, and they were able to predict it very correctly over, average over long term, not short term. And they just, show to Earth, and it's like they basically predict the ocean's temperature over a long period of time very, very well using Fourier neural operator. And I think that is an impossible simulation task usually because it's very expensive to simulate multi-scale physics over billion of years. Okay. I mean, stuff you guys learn is going to be super useful on all kinds of things. We are working on oceanography. That's what I know about this. Yeah. Any other questions? No? All right. You guys, great. Feel free to ask questions. I'm trying to be approachable, so don't. Yeah.
In the graph setting, did you also add noise to the
I
structure?
can't hear you.
Yeah, sorry. In the graph setting, did you also add the noise to the structure of the graph?
Oh, to the structure of the graph, not to the structure of the graph. We did
just to the node features.
Node and edge features. Yeah, we did not add to the structure of the graph. There is a question of whether you should add extra nodes, right? So we wanted to find the planet X. I don't know if anyone who knows what planet X is. Do you want to say a few words about planet X for those who know? I've been talking nonstop for the last half an hour. Speak up though.
I'm probably though not the best one to talk about this, but yeah, it's kind of cool. So there have been like perturbations in Kuiper objects that are like not, I think, really explainable with the gravitational influence of what we're tracking right now. So one hypothesis is that there is a very far away planet with a very, very long orbital time. So yeah, we just kind of, it moves so slowly on the sky that we haven't spotted it yet as a planet. And there's kind of cool research that tries to infer the position of this and observe it somehow.
Yep, exactly. So people can use NASA data, and we actually have used NASA data observations of all the planets in the solar system, like about 31 of them, not all of them, and the moons, and trying to figure out if I put an extra node, can I find planet X? We did not find it. But you can add nodes to it, for example, and add extra edges that you might not need, but it gets slower as you increase complexity of your network. So it's the choice about runtime too. All right. This is the one that we accelerated a million times. Here is a universe that's at 3 billion years old, and the blue points are these things called dark matter. If you actually watch Marvel Universe movie, they mentioned it, so it's real. Also, they also have dark energy. It's also real. Because Marvel Universe first, I think the first Iron Man movie that had joint dark energy mission blowing up in the beginning of the movie. Joint dark energy mission is real. The blowing up part, hopefully not. And and dark energy is about 70% of the universe. Dark matter is about 25% of the universe. The stuff that makes up you and me and everything else is about 5%. That's what we think. We might be smoking a lot of things, but it is what we think is happening. So the blue dots are these 25% of dark matter that's around. All these other stuff, gas, like gas, it means hydrogen and all the other stuff is showing up here. And we were able to simulate this universe. This one took 300 million CPU hours to run, like for real. And it shows less than 1,000th volume of the universe. This is just a picture of a zoom in version, but the whole simulation project is about 300 million CPU hours. And it showed less than 1,000th of the observable universe. And we did not simulate everything using the, machine learning. We only simulated the dark matter part, which is just gravity with dark matter and dark energy, stuff that we don't know anything about. And we were able to do it about 1 million times faster. So with machine learning, and it's very simple things using UNet, but that was like way back in the days. We started like 2017 when people weren't even thinking about it. People know what UNet is? Some nodding head. Okay, people nod at heads. Can you explain it? Who hasn't spoken yet today? I'm gonna point at people. Okay, people with the cap.
Well, not an expert, but it's
Can you just speak up? It's okay. Nobody's an expert really in machine learning. You feel like they only know something they work on.
A neural network that works on voxels.
Works on what?
Voxels,
I can't hear you.
like three pixels.
In what pixels?
Voxels.
In voxels, yes. They do work on voxels. What else do you know about the shape? What is it called? UNet. Please, come on.
The shape it's just a unit, like you up here, you're down.
You have to speak up. I'm terrible at hearing.
The shape it's just a U where you have the upsampling and the downsampling layer with your latent space at the bottom.
So she knows, but can you guys hear her though? Yes. So no. You want to use my mic? That's all I can offer.
I'm saying like the unit, it's just like this where I'm not sure if this is the downsampling and then the upsampling layer, and then you have your latent space here. Instead of like an autoencoder has like your encoder here and then your latent space here and then your decoder here, but this one is like this way.
All right. Applause on this one because people usually don't know why these things are named certain ways. So this one is the obvious thing, which is really good. It was used for segmentation for medical imaging originally. And it has the input and the output the same size. And it works on voxels or grid cells. And the cool thing about this is that it actually is great for multi-scale physics for some unknown reasons, which hopefully you guys will find. That one I think I might know the answer. And you guys will work on it later on today. So that's cool. Here, then you can also use machine learning to assist scientific discovery. Here, you heard from Miles, right? So this is unsupervised resource allocation instead of using reinforcement learning, using graph neural network. And I thought that was cool that we can do reinforcement learning like things, which is us figuring what resources we should put in what things to run experiments. Instead of using reinforcement learning, we use graphical neural network, and it works pretty well. But we can do that. And what Miles had done here with Peter McCurry and Brian Nord is that you take the ground truth of these observations, you kind of blur it, you don't know what it is. You have an initial observation that's super noisy of the sky. Then you use a GNN to model it. Well, traditional sampling can sample, like decide which galaxy you want to observe. Then you use a GNN to decide which galaxy to observe instead of using reinforcement learning. So there's another thing to think about is that you can use a network architecture for very many different things. Like, I never expected GNN to do something like reinforcement learning before this project, for example. Cool. Here is another one. Okay, this is Giuseppe's paper. Can you help me out with this, Domenico? Have you guys heard Giuseppe's lecture? Have you seen this? Can you guys explain it to me? Because I honestly don't know enough quantum.
Well, essentially, the idea is to represent the wave function, the parameters in the wave function. These are variational wave function that you can optimize the parameter with the neural networks.
Yeah.
So essentially, these are correlated systems. So correlated means no interaction between the electrons, and you need specific and peculiar wave function to describe properly the interactions.
But you learn the wave functions?
Yeah, you learn
the representation.
The representation, the parameters. So you optimize the parameters of the wave function.
But you optimize the parameters of the wave. Okay. Because I was curious if we can run PySer on this and do symbolic regression on these representation. Another research project. I'll ask Giuseppe later.
You have to ask Giuseppe. Yeah.
Sorry. This is another project. I was like, oh, maybe we can do that. Because you guys learn PySer, right? So in principle, you can, if you can sparsify the network enough, you can interpret what the network has learned. And these one are parameters of a wave functions. Maybe. Okay. Because I think one of you are doing action angles. Actually, Amaya is doing action angles. This is very related, like what I just said. You can figure out these action angles with neural network and interpret it. Be pretty cool. Apply to quantum mechanics. There's inference. I don't know how many of you guys have heard of a recurrent inference machine. This is Maxwelling stuff. No? Yes? All right. Give you guys 2 minutes to search it because this is a pretty big paper. I'm sad you guys haven't heard of it yet. It's for anyone who do inference. It's actually pretty cool. In this case, we here, it's not me, it's actually people who were postdoc here before. We constructed gravitational lensed galaxies with recurrence inference machines. It will show up in arXiv very quickly. People who are not Googling, do you know it already?
I'm in Max's group, so.
Oh, so you should tell us, please. I know one of you in Max's group. I just don't know which one.
Yeah, so
if it's wrong, you can report to Max.
Okay, yeah. I mean, it's not recording. So I guess if you have a noise model of your telescope, for example, then getting kind of the posterior, let's say X is the target image that you want to obtain, and Y is the noisy one. Then you want to maximize P of X given Y, because Y you have the noisy version. That is using base rule P of Y given X times P of X. P of Y given X is your noise model, like your telescope. And then, so if you want to do gradient descent on this, then you have the gradient of P of X. This one you don't know, but you learn basically the gradient using your model. And so you apply recurrently this learned gradient. So the model learns the gradient of P of X.
Excellent.
I know, yeah.
No, this is good. But if you guys don't know what that is, you can bug him. Now you know. Cool. But it is the first time people use sort of like neural network architecture to do inference in this way. It's actually very new when people have used it. And I didn't expect, this recurrence network would actually be useful for this particular method. We can also use machine learning to obtain models that are physically understandable. This is Schmidt and Lips in 2009 before deep learning existed, right? So they ran a very, very small neural network, and then they have simulated of this pendulum, and they were able to recover like Hamiltonian Lagrangian for those who have studied some physics. These are conserved quantities of a system. And it was pretty cool back in the days. It's actually a science paper because no one were able to find something new or understandable in neural network. And at that time, neural networks don't work as well. So.
Is this using symbolic?
Yeah, they use symbolic regression. So we actually this was the paper that inspired Miles and I to start looking at this. So Miles and I independently got really interested about this, and when he came to Princeton as a grad student, we were like, okay, let's do this. And we were very excited about the idea of possible symbolic regression and how that could work with neural network. But at that time, neural networks are not neural networks you know right now. And they also are not very good. The package is sold to a private company, so you can't actually access it. And we just rewrote a whole package, and it works well that now we can combine it with neural network and do the correct regularization to sparsify the network. That's the contribution we made for the NeRFs paper. Other questions?
What do you mean by good regularization?
That's another paper. So we have many different ways to sparsify the network. And the network in our case was a graph neural network. And we try to minimize the number of message elements, number of elements in the edge function, in the edge vector. And that's, how do you do that, right? And so we try a bunch of different methods. It turns out L1 is okay for that particular paper and for that particular problem. But we find out that you have to do a lot more different things for much more complex systems. And then we invented a different network to do it. Okay. Oh, wow, we're actually going pretty slowly. I just realized. This is Cindy. For those who have done a bunch of symbolic regression, these are the people who have been doing symbolic regression type of work, genetic algorithm work for a long time, to try to figure out how to use machine learning to obtain models that are physically understandable. And they have like the way to try to make an equation. Like, how do you pick an equation, right? Many equations will fit the observable. So how do you pick one that is it the least complex one? But there's a curve they always think about, which is how well it fits. So dropping is the error, complexity going this way. So like, when do you pick the right equation? Because the more complex the equation is, you can have much better fit. Just in generally true. So when do you stop? Which equation do you pick? So that's actually a lot of work that went into this without, us. This is pioneers. We also had our NeRFs paper 2020, which actually combined graph neural network, regularize it in a way that's making it sparsify enough to run it through symbolic regression. And we created our own symbolic regression package that you guys have run already. Yep, awesome. So physics for ML. I'm not going to go through all this because I actually don't know as much, but a lot of people took physics ideas into machine learning. Clebsch-Gordon coefficients, stuff that we have done a lot of calculations in physics 101. They actually just put it into the machine learning one and say, hey, I have created a new neural network that obey this particular symmetry or these particular properties. Tensor field networks, rotation and translation equivariant neural network for 3D point clouds. A lot of these ideas came from physics. So I think there's a lot of interest in that direction as well. This one is a steerable equivariant graph neural network that are very the physics ideas are all everywhere. Like what kind of steerable, and this waveless scattering transform is also similar in a way that we use symmetries and ideas and inductive biases of this physical data and then try to create a network that respects it. And people think that these will reduce the amount of data you need to train the network and make it more efficient to train. And that's why they create this network that you should beat, not always, sometimes beat the state of the art, but not all of them. We created one that you guys are going to run later today, the Lagrange neural network. That's we wrote 2020, and it's actually inspired by Sam Grandena's Hamiltonian neural network 2019. That was both NeRFs paper. This is Rose Yu's paper. Yes, this is Rose Yu's group's paper, and they show that you can actually do very many different possible ways of doing turbulence simulation accelerations. These are all the different ones above with different network architecture. And what they did is that they do a temporal filter and a spatial filter. So the idea of doing temporal and spatial filter came from what the turbulence is doing. And then they create a network that's basically UNet architecture with temporal filter, spatial filter, and the rest, and combine them together. And that's what you see at the bottom, like right here. So it has like UNet connected across, and it made better predictions. All right. I'm not gonna go through this because you've seen this before, but you should ask me and Miles to give you guys one time just on like symbolic regression what we have done, because we've done pretty cool stuff. Okay, so I'm not gonna go through all this now, what we have talked about, but I would like to say if there are any more questions. If not, we're gonna go to Colab notebook. No questions? Yes.
I think this is not really like well developed, but do you know if people are working on like theorem provers using like machine
I
learning?
can't hear you.
Do you know if people are working on like theorem provers and like
Yes, yes. And you know, and Akuma's group does that. They like to prove theorems with machine learning and solve equations with machine learning. So there's a whole area of that, even though she like directs the NVIDIA AI, but I think her gist of research is actually not on the robotics and stuff, but more like theory proving.
okay. Do you know if those are they will work well yet or like how long it would take? Those two.
I will talk more when it's not recorded on this.
Okay.
Yes.
What are kind of some of like the open questions in like some of the work that you presented, like turbulence simulations? Like, what are people thinking about now that we have these models already? Apart from interpretability, like I know that's like a big thing that's throughout ML, but like specifically from like a physics perspective.
Yeah, from the physics perspective, I think prediction of posterior of predictions in high dimensional space is very hard. So, you know, you can probably heard of multi-swag or swag, like these BNN, Bayesian neural network methods, or you can do MC dropout for the simplest one, right, for example. And they actually, our group have done it with just a Gaussian data set, very simple ones, which we know the error because it's Gaussian, and it does not reproduce the correct errors, none of them. So then, you know, that's an open problem for you or for anyone who's interested. I think it's truly important for the scientists because we need the errors when you predict something. Or even for the medical field, right? If someone tells you you have cancer in 3 years, is it a 5% error bar or is it 100% error bar? It makes a huge difference how I plan my next 3 years. So, you know, there are a lot of interest in that direction too. So interpretability is obvious, but the error prediction or posterior prediction is actually really hard. And I think there's active research in this, and it's really in vogue in last about year or two, I think, or maybe 3 years. Yeah, that's another one I will be very excited about to learn. And a lot of these simulation acceleration stuff are not perfect yet. I don't know if you noticed these simulations that we show you. I mean, the turbulence simulations we used are very low resolution. The people who care about turbulence want to run, you know, 1024 cube or more, or 2048. I mean, I know people, some of you do this here. You don't care about, you know, 128 cube or 64 cube simulations. So how do we do that big data set in such a small GPUs when you look at the data set? And that's somewhat engineering, but I think there must be a smarter way to do this than just software engineering the heck out of it, which is another way to do it. So admittedly, we actually software engineering our stuff the way so that it is 1024 cube in our like simulation of the universe. We actually made it really hard to make it work, but software engineering at that point. All right, can you form your working group? Like 3 to 4 people. You can just sit closer. Just know we're gonna have reports from your group when we have questions. I mean, preferably don't hate the person you're in your group, and no fight should break out. I'll tell you stories about my grad school days when people had fights breaking out over maybe another dinner. All right, everyone good? Yeah? All right. Can you load Google Colab? You can go to this. I can send it on the link. I don't know how I can, is there a way? Can you guys type it and copy it enough to, this is just the UNet. For those who have done this, try to do the extra time ones and give me explanations why and what you expect to happen. People who haven't done this, try to download the Google Colab and run it. And this will give you a sense of like A, how to run Google Colab, you know, how to use Google Colab, B, you know, how to run a fairly simple neural network. And this simple neural network actually is very useful. It is a UNet architecture we talked about several times today. So let's take a 5-minute break just to see if people get the Google Colab running. It's also to make sure everyone can work on Google Colab quickly. A simple version would work. Make sure you know which one runtime you want. You know, are you running on GPU or CPU will be super slow? People who don't use Google Colab might need some help. I can walk around. We'll take 5 minutes to look at Google Colab. For people who are very familiar with this, try to modify a network, do the following things: change the number of layers, give me an expectation what will happen when you change the number of layers, remove the skip connections in UNet. And if you don't know what skip connections are, we'll talk about it later, actually, towards later. And tell me what you expect when you remove skip connections. Removing 1, removing 2, removing 3, what happens? When you change the loss function, what kind of loss function would you add to it? Is there some interesting things you want to add to loss function? So for those who are advanced-ish, like do the extra time parts, and do give me an expectation, not just like do it, right? Give me an explanation why you think something will happen or something won't happen. For people who haven't done it, let's just try to do it. I'll walk around and see how people are doing, and then we'll ask for reports from each group in 5 minutes.
It wouldn't be useless for me to do it.
It's just NumPy. So I guess the model definitions. Model definitions in cell 8. So we can just change this. These layers. Well, which layer do you want to remove? So I guess the output size and input size are kind of like,
Ja, diese Unit-Architektur.
so
Das State für das Task.
aber das sagt genau, wie viel Informationen wir dürfen.
Are you guys able to run it first?
Con.
Yeah, open it in Colab. Yeah.
Yes, it's very good.
So
Oh,
actually, I don't really understand ResNets very
Yeah,
many of these things really well, but so I don't have an
Time to run. It doesn't
Yes,
run
we're
instantly.
changing the matter.
Like read the Colab a little bit. Like look at the
Yeah.
code and see what it does.
So it's supposed
It's
to get
actually
better.
quite well written.
Ideally, yes. Increase it. Yeah, but also like
Those who already
increasing-
know how to do it, can you explain the skip connections? What happens when you cut it? Like you change the architecture.
Are you guys able to run it?
Yeah. So what are the things?
Those who haven't done it, like take a look what it's
kind of fun.
doing. And then
Like think about it's really easy to optimize like a linear
Start a
regression.
new project.
Sorry. Wait, what?
I'm
What do you
kidding.
mean?
I'm kidding.
Oh,
It's
okay.
like, yes,
Sorry.
talk. Do you guys have ideas what happen when you change your architecture? Because people use the network, they don't usually ask what happened. It's probably when they change things. So
Well, yeah, we were just talking about
Mhm.
yeah, like changing the number of layers is like changing the number of parameters.
yes,
I
but
feel like
then you
there's
can
something
just
deeper,
change.
probably.
Yeah, does it have to be deep or does it
Right,
just have
like
to be a
deep versus
number of
wide.
parameters, right?
Yeah.
I think each group will want to report some of these stuff. So, but let's just make sure everyone runs it first.
Oh, okay. So like this, I can give you like a really good example.
Do you guys have any
You take
issues in
linear
running it?
regression, right? We know it's convex, so we can always like converge to this thing. But consider instead, you have like a 2-layer neural network with no activation. So this is also linear. But now the optimization is not convex.
Oh, no.
I don't know.
They might not run UNet though. They max it.
Why
It
not?
has to be equivariant.
Aren't linear networks convex too? Yeah, but the thing is, your parameter space is now 2 matrices.
You guys know.
So let's say like
But you're saying that's not convex.
that's not convex.
Do you not know?
I can show you why.
Try to run it because
But
it tells
it's
you
not-
like
I let you
what
think
you
about
need to import and all that.
So your 2-layer
I think
neural
you've probably
network,
done it.
even without any
Yeah,
activation,
but not in Python.
is not easy.
Yeah, maybe not in
Your
Google
optimization
Colab.
is
That's
really
another thing.
harder.
You might have run it on the local cluster, but not on Colab.
That's true. That's true.
No, a lot of people actually do not know this. Like a 2-layer linear network is not convex. Even though the
Doesn't it depend
Cluster access, so you guys have to use a lot.
no, it doesn't.
Guys,
I thought auto encoders were
guys.
like a linear, fully connected linear auto.
Not
Yeah.
yet.
Do you have any idea what
It's not.
like a super general question, but what's the implementation? I don't get it. Like, what's how do we?
These are the.
We're just running it.
So I flashed the first question. I expect people to answer from the group in 5 minutes.
So I give you this image.
Yeah.
Tell me like which pixels belong to which object.
Okay.
So here like the green pixels belong to this triangle. So that's why they're in one color. The ring, the pixels belong.
So I truly hope this group will go out and say, I understand the network not just to run a bunch of, things that downloaded online, but actually have some fundamental
That's why we
understanding.
don't accent the tensor shape. Now I'm getting what it means.
Where do the colors matter?
Oh no, the color is just like a symbolic. Yeah, exactly. So then it's still each object.
But in this case, can't you just say, well, everything that's white and glows together is one object, and everything in black is
Oh yeah, I mean this is like a really simple example in which normally you would have like just have like a picture of a person, and you would say like tell me all the pixels that belong to it. This is like a really simple example.
So I think I should.
Yeah. There's like
Should we add more?
I don't know anything about that.
Like every pixel you're predicting like a 6-way.
Okay, so maybe let's like, maybe give me an example, something.
Yeah, it depends on
So
the
they
problem
have a new
itself.
project and just works.
Why do you think this?
Because then each pixel I'm going to label one of 6
Data.
ways.
Oh,
It's about so it's predetermined that it's 6 different things.
But through
Is this the function that defines the
In some ways, like all the numbers are some ways
which makes no sense because so I have it through my Princeton account.
But this is a limitation.
To Princeton, like to the Princeton.
I'm slightly confused by this
Or to supply
yeah.
shape. I almost have resources here, so I'm trying to figure out what I think I'll just try like de-identify.
Yeah, it should just be like 0, 1, right? Like
Yeah, 0 like
I can't imagine because I just talk to
where do you see output?
I need to get the shape. Like it's the very first line almost. Input mask shape.
No, so we're gonna have to de-identify.
It's like we could take external maybe we
I guess the connections are like it doesn't like
There won't be like people names, but I
Oh,
think.
you're saying you can just compress 6 dimensions.
Yeah,
That's
running
kind
it
of
and
what
then
the
try, and I think that's just.
The model also.
Because we need to take it offline, just like big comments out, it has to be.
that would make sense. I think considering honestly the network physics, what coding is then
And I wanted to see also, I don't know how much
The
meta.
colors are not important. They're not inherent like
So it'd be cool if we could, color some of those plots by like.
Change the loss function.
Or geographic
Yeah,
location, I was just hoping to mix some plots and see what we find, because I think a lot of it just selection bias. So the first thing to know is like, exactly, the students understand what we do, and I'm like, that's going to hot pots, so that's gonna be a lot.
So the network is trained to like segment this image, like isolate each individual shapes.
So for each pixel, predict which object it belongs.
There's like a new release,
Oh.
this release of the 4th cohort just came out in December.
Oh, I see.
But another one of Olga's grad students, a first year grad
You can
student,
always
was
ask,
gonna start playing with it too. So we have a few people that can try to figure out, because I'm learning all this stuff. I started to read the papers at the end of it, I was like, what the heck? And autism is a really complicated. I used to babysit autistic kids, I have some.
How long does the training take? I thought it was the opposite.
And it's a super
Oh,
heavy.
okay, sorry. When did we start? Because it's 2 minutes.
I'm actually curious, like personally, just my husband's nephew also.
This is like a free Colab out there.
Yeah.
Yeah.
Yeah. The genetics are very complicated. Yeah, it's very messy.
I read one paper.
Yeah.
Like they're so clean.
Biology is a complete mess. Nothing makes sense. Yeah, it's so hard.
When do you think, what do you expect, like,
I know.
in terms of
Sometimes I'm
like the
jealous of
output
people
or
in
like
other
in terms
fields.
of
Their
like the
data is
training
so much
process?
cleaner.
Well, it's obviously they're much
I mean,
slower.
I'm still here.
Like
I still
accurate-
like it.
Like
just,
accuracy.
you know,
Yeah,
there are days.
I think if you have a
All
bigger,
right,
like,
anyone want to report?
you have a wide layer.
Actually, for each group, you guys should rotate the reporter if you can. On each of the questions, we have like 2 more questions, and then we have another Colab notebook we want to play with.
I don't know. But
Have people try to change the number of layers and see what happens when you run it. Some people who's never done this before doesn't even know how to change the layers. This is like the crazy thing.
oh, so it is
I think we need a bit more time.
And try to help each other, don't kill each other.
it's still going.
So another 2 minutes. Is there groups who want to report on what's the effect of changing the number of layers?
Yeah.
Okay, I think what we should do is like everybody run like one and
No
one.
one's responding.
No response. They're
I'll
all
just go
very
ask.
busy.
Okay, so wait, yes,
But I guess you could still just pick the maximum.
Mine went really fast.
And for the first time, we haven't changed.
Yeah, okay, we'll wait a little bit more, still running. Is yours training yet?
I mean, to be honest, I could run this on my
running
like
GPUs,
my
not the CPU.
internal Colab.
It's the runtime.
Oh, no. Inside Google, we have like.
Are you running this? Oh, but you should use Qt, the same report using Qt.
Well, we always
You wanna make sure it's,
you work with
so there's a place where you wanna change the runtime to
Is the network
GPU.
pre-trained?
So where is your manage sections?
No, I think we
No,
are
we have to
training
train
from
it.
scratch.
But what are these like
No, that's fine. You have
44?
So don't
megabytes
run
that
it
we're
on
loading
CPU, so the first thing. Make sure you change your runtime on the right machine. Sometimes it's good to check whether it's running on Tesla T4 or whatever is running, right? So if you're running slow, like check.
Maybe we're like fine tuning it.
Properly.
That makes sense.
But no, it's not.
Change the number of layers. Yeah. Alright, tell me what's allowed. You can do a neural network architecture search, but not experiments.
How do you? I don't know.
I
think like
Have you tried changing the
Yeah, I
A
guess.
lot of the newer generations don't know how to do this.
You might have not just like.
What are you?
Guess the rest. Maybe this is just the rest.
I think it's fine.
Change the number of layers, but I also have like,
Yeah.
I was
Yeah.
going through all the other.
and then
steps.
when you change the number of layers, there's a bunch of things to
I
move,
just
so
didn't
be
start
careful, right? Like not just one line.
Yeah, you have to comment it out every.
Yeah, they have to comment it out appropriately, otherwise it will crash.
Did they change? I guess it's on 4 out of 9. That's not that bad.
Did you already change
Yeah,
commenting out.
Cool, what do you change? You remove one of the regular. What would you remove it? Or would you change it to something else? Yeah, have you removed some layers? Increase some layers? Yeah, set it to GPU runtime, it's on top. Yeah, they will
You have a base run, right? Reducing the base run.
Yeah, reducing or increasing the layers and know what to
Do
Also
some
part of
more.
learning how to use Colab. How's everyone here?
Oh, you have to switch like
You
layer.
switch all the layer tiers out for layer 1.
I think I'm on the GPU though. Like I don't know.
Some of the
I
GPUs are
You can
much
do.
slower
would
than
Just
the
make
rather
the
other
layer
ones.
as identity.
Like I did.
Oh,
this
that's smart.
step. Does
Yeah.
that mean it's
Okay,
not
that's
smart?
You're on test
Okay,
before.
yeah, okay, so it's not taking
Oh,
that long,
that's a good idea.
but
Yeah, it would take
Nee,
some
aber
time.
kein
I would say it's
Problem.
really
Weil es definitiv für Leute angucken, oder ist das
we're a little unsure, like,
ja, das ist generell
where
hier. Ich glaube,
we
in
would
Practice,
change
in
the
Practice
number.
sind das hier
Yeah,
mit Residents.
so- Oh, your friends is.
When I run calculators,
Nee, es ist so, ja, das ist halt Convolution. Ich glaube,
See
Are we
here.
really changing it here?
no, but it's still
Yeah,
good
you
to
can change it within the rest unit class.
I have to exempt it from.
But would you also change
Yeah,
it in
it
the
should have any
forward?
parameters. Like an in that identity. Or
This is where in class.
It won't have any parameters.
This is actually.
If
Right,
it doesn't have any
But
parameters,
if you
like.
change it here, would you also need
Okay,
to change
yeah.
it?
Usually you call here, right? Later on you call
No,
this
but
class,
this is-
essentially this class, and you don't have to change it. Once you change it.
What's the point
Okay.
of this function?
Oh, there's a form and there's the part that you go down
Social laws.
and then the part you go up.
You heard of that one?
So probably wanna take a look
Oh, we
at
don't get like an
the,
activist metric.
where's the Google.
Oh, that's switching.
You wanna take a look at it. Explains the network architecture, they actually plot it for you. Go back one more, yeah.
Yeah, what's the base model? I'm not getting that part.
Oh,
I'll
I just have
just
to
go to
type
like
it in.
it.
Yeah, and that one actually shows you what the network is like. And you wanna see how that network picture relates to all the layers that you see. So here, actually, some plotted, you printed it.
Yep.
What they are, I mean, you don't wanna
Ah,
be
so they
like,
just
people
extract
who
like some
run your
layers
network,
out
they
from
don't
the.
know anything
Like
about
some pre-trained
this.
layers.
Oh, they're pre-trained.
Yeah. I
So
see.
some of the
So
layers are.
now-
Oh my god.
When you go down
And
here,
some
though,
of
this
them
is
we-
just image masking for training.
Oh, that's confusing.
And then
Which
prepare
ones
data
can we
sets
train
and loading. It talks
So
about
you
what
see, like,
everything
the,
is. Now it's create a unit model. So it talks about unit model. Well, this is just for
Self dot
training.
layer 0.
Yeah.
But then wait, there's a better version of this.
Where are you at?
Just go to cell 8 when you define a unit model. Go on.
Cell 8, other numbers.
It's changed.
Where's cell 8 here?
Okay, you might have.
That's the network architecture they actually show you. And it will match
Oh, wait, where
what
was
he
it?
printed.
Are these
Oh,
So
this
here,
one,
yeah,
layers?
this is yeah, so these are the layers.
Okay.
Base
And then
model.
this is the skip connections.
Yeah, this is.
And this is the U shape
This is like a
that
pre-trained
Massimo
resident.
just talked about.
And you extract some
And
of
then
the
you can try to change layers, and then you want to go back to the code and say, okay, what the heck is going on?
But some of them are
Hard
like
to read all of them. Define
you look
unit
at the
model,
1
and
cross
you
1
try to say,
model,
okay, here's the base
those are like
model,
our
base
own
layer. So layer
layers.
one, which layer is that? Just think about it. Look at the code.
Yeah,
The next one, this is remove. Remove is this activation function that you probably read about. So
I don't
you have to
know
go
how
through it a little bit. I
how to
think that's
change it
partially
within
why I
the,
want you guys to take a look at actual neural network.
Yeah,
Yeah, take a look at you found this one. Right?
well, here.
Most of them knows. You can just ask her.
Like these, right?
Well,
So
yeah,
it's
I think it's
like
I know you've worked on
you
your
just like
network.
let it equal.
Yeah.
Oh, is that part of the torch there?
Yeah, yeah. And then
I've never seen that.
well, what you can do.
Probably not.
Why are we doing this with
No, that's why you pre-train a lesson.
This addition.
What are we comparing?
Part of the,
I need to be able to know what changes I do. Like, are we gonna just review?
Yeah, I see, it's basically like all.
Oh, wait, what's that?
yeah, it only takes the first layer.
Okay.
Yeah, so all of these are.
Oh, my outfit just looks really different.
Yeah, because it's.
I'm aware.
It's just.
Okay.
So sequential generates these phase
Oh, I see, that's why this is not like perfect.
We're supposed to do 4 days a week.
So each of these is.
So they're pretty close, but like the triangles don't look.
Don't we have to look at the input and output payments?
Yeah, it's just like zip there, and I have a listening appointment. Oh, you have 3 appointments.
Okay, let's just take out a layer.
But I don't like NYU so much.
Maybe we
Yeah, this one.
when you change the number of layers, you are like
Comment.
Just comment layer 4.
I don't know. I think so. Well, why does this one? Why does this one not have something with a 4? Like, do I need to comment on what the three is so I know how to look at it now? Then I
Once you're, are they
All of this is what's in the base layer. It's something that
No, it's not just you. We have issues.
basically
looking at this resume unit, the issue part, seeing it seems like this
Then I also, there's gotta be a way. Yeah. Also, we don't have blackboards and whiteboards in the office.
there were actually some students that just jamming, and I also just
When I understood
they're at the Harvard. Yeah, yeah. You know, yeah, so this gets totally it's just there was also this really this thing just all of us really exist.
How's everybody? Raise your hands when you finish running the collab the first round. All right, not everyone, okay, but most of you. Raise your hand if you change the number of layers and still be able to run the code. Nobody. Okay, this is good. That means not everyone thinks, not everyone knows as much as they think they know, which is always the case in machine learning. Because once people ask you to change the network that you're given, it's much harder. I mean, try to download a transformer and mess inside, right? But this is good. I have 40 more minutes of lectures. I don't think you want to sit through it. But I would encourage you guys to do this, and you can do it as homework. We can try to do something else next week or Friday. But I can also just suggest learn to remove what skip connections are. I'm just quickly flash the slides. What do you expect will happen? What does it mean to remove skip connections? Skip connections are those that is concatenation. They basically copy over. Like what does this do? This is actually very important. If you cut it, something fails dramatically in UNet. Like all the stuff I've done, if you cut them or you don't cut them, it makes a difference quite dramatically. Go ahead.
Well, it's simply not a unit then anymore, right?
Well, we've only cut one of them,
Okay.
not 2 or 3.
Okay.
So actually we have one of the architecture, we only cut one and cannot cut more, and it just, yeah. So it depends on the data set too, obviously, but it'll be good to think about them. Changing the loss function, I want you guys to think about what changes the loss function can you come up with? Not just, if you do a regularizer, like what do you want to change? Is this something about conserved quantities? Is this something that you would have checked if the output is correct? Do you want to put into the loss function? So in astrophysics, we would check something like the correlation function or the power spectrum. Should we put it inside the loss function if you can compute it quickly? How about some symmetry stuff, like you enforce it to be, I don't know, conserving angular momentum or something like that, or conserving the energy, or conserving the number of people who went into the party if it's a graph network with lots of people running around. Right, so think about that. I was gonna talk about inductive biases and whatnot with a different collab, but I think I will stop for now. I'll share the slides. I'll just send it to you guys on the email today, and you can go through it. At least the collab notebook will talk about the collab notebook actually for the Lagrangian neural network, which is a symmetry. This is something that we talked about, like physics symmetry in part in inductive bias into the network design. So I thought it would be cool if you guys run also a tutorial for LNN. You might not have time, so I'll just send the slide to you guys. These are the tasks to do for the Lagrangian neural network parts. And then I have another 40 minutes of slides, which I don't have to talk about. But I'll send you the slide and see if people want to talk, we can talk more. We can arrange another lecture next week. People are tired because we have so much time together anyways. I'm around. But I want to see people who were able to do the Colab notebook before I go further. At least the first Colab notebook. So yeah.
Could you repeat for what kind of astro data you use UNet?
Oh yeah, we did a lot. The a million times simulation acceleration was just a simple UNet. Everyone was always shocked when we did it. What Kimberly Stechenfeld had done for this turbulence simulation, it was like a dilated residual neural network that looks like also like a UNet actually. It's like residual neural with the U shape also. And then we also did it with anything that have the same shape of output and input. A lot of the times are dilated residual neural network or UNet type stuff.
Simulation is a dynamic, no? So you have initial condition, then you run for a step, and then
you loop back.
You look back. So the output becomes the input.
Yep.
And so the block is always the UNet.
Yeah. It's pretty crazy. All right. So I will just let you guys do the Colab notebook. You can do it at home, but I would love to see what people come up with. Maybe I can just arrange another lecture next week when people are more spread out. Because I think you can't do both Colab notebooks so quickly. And do answer the questions, because then you can tell people you actually understand a little bit about neural network. All right. Any questions? I just want to give some time for questions before we end today. It's nearly 5. Do you have to worry if your Colab notebook doesn't run? It's okay. You just need to make sure to use the right runtime setup. We'll try to get you Colab Pro, but it doesn't make a huge difference for what you're doing right now. Any other questions? Everyone's trying to figure out how it works or all on Twitch. I'll be shocked if someone who doesn't know what Twitch is, who's here. All right. Anything else? Well, if not, we'll arrange something maybe next week so that people can come back to it after you've done some Colab notebook. I'll send the slides out. But if you want to quickly download this is the Colab notebook for the Lagrangian neural network. But all you need to do is actually search Lagrangian neural network, and you'll find it. It's actually Miles and Sam Grandanas and us wrote the paper, and it should show up in Sam Grandanas' blog, the Colab notebook. And so she tried to run it, and the questions are, what happens if you replace Lagrangian with Hamiltonians? Can you change it? That's a harder question than what you had dealt with before, because that really changed your network to a different sort of like conserved quantities to base a network on. Honestly, if you were able to run the neural network for the UNet, a lot of you guys' project probably is already halfway done. Maybe it's already done. All right. Anything else? Is there a topic you guys haven't covered that you're interested in?
Simulation based graph neural networks, I guess.
You did not do graph neural network. We can do graph neural network easily. What else?
Simulation-based inference, maybe?
We can talk about simulation-based. How many people are interested in what they just talked about? Okay, people interested in graph network, raise your hands. All right, we should probably do that. People want to do what? Have you heard of simulation-based inference? No. So some of them haven't. So they don't really know what simulation-based inference. We can probably arrange something for like future several weeks to cover these things, because we have experts in here, so we can just arrange something. Miles and I can easily cover graph neural network. Actually, Serv Ash and a bunch of people in CCN probably curious about covering graph neural network. We can do simulation-based inference in definitely astrophysics context, which people claim we are one of the experts, in the world. But there is a lot of simulation-based inference work in science. So I wonder who else we should rope in.
Anyone in CCB?
Yeah.
Maybe neural architecture search.
Neural architecture search, that requires some significant undertaking in this crowd. Who knows what NAS is? Raise your hands. Like 2 people. Okay.
Frank might talk a little bit about it tomorrow, but I don't know how much.
Yeah, so Frank is gonna cover neuroarchitecture search a little bit. That'll be fun. We have a project on neuroarchitecture search, but I feel like it's much more of a discussion than a lecture. It's much more intense, I think, than UNet. Anything else you guys want to cover or hear about? We can also get like a talk, but not a lecture style on some of these topics. That could be more interesting for those who are slightly more advanced. Anything else? I got graph network, graph neural network, simulation-based inference, and neural architecture search. We can just get a few talks. And there are people actually giving talks in journal clubs around in Flatiron Institute. Maybe you guys should just pay attention. These journal clubs happen. So we cover some of these topics already several times. Okay. Anything else you guys want? Anything you hate about the program so far should let me know. Maybe secretly, not in recorded section. But anything you'd like to add or not add? Because we try to do it, might try to do it next year. So like, tell me if there's something you want to improve. We might do like a survey that's anonymous at the end, but if there's something that can improve for you guys now, you probably want to say it. You have terrible food. You don't know what to do with yourself.
You can tell any of us privately also. If
Yeah,
don't
you
wanna
can also
say it
tell
in front
us
of everyone.
privately if you want, or we can also
Maybe one problem will be desks in our centers or institutes. So find a place where they can stay that is not just the dining room on the
Do-
floor.
Do you guys like the dining room so far, or are you okay? Like just take over 3-4 rows of tables.
There's also room on the 7th floor with some tables. If anyone wants to work there, there's usually not many people there. Just like wander around the floors and find an empty table. No one's gonna kick you out.
Yeah, they will just pretend you're working really hard. No one's gonna talk to you.
As long as you're not like loud and disruptive, no one's gonna do anything.
Yeah, it's also because summer people are traveling, so there's a lot more like empty space than usual. But if you do truly want like a collaborative space, we can probably find something for you, but not like permanently you like take over that space because we have a lot of workshops going on in summer. Actually, we should check if we can like have some of these bigger classroom for them and see if we can find something over.
Whenever they're open, yeah.
Yeah, like here, I think they're not running too much stuff like, or maybe over in on the other side. Anything else? Don't be shy. You can also tell your mentor what you hate or dislike that we can change because we can still change it. You're only 2 weeks into the program.
Not even 2 weeks.
Yeah.
Not even 2 weeks, like 10 days into the program. Okay. I was thinking, what are your social programs? Have you guys got the social program list yet? Do you guys know what you guys are doing for like social stuff?
Oh, there was someone just mentioned on Slack that there's like a visit to the American Museum of Natural History that everyone's been invited to. Is that?
Are you guys aware of
everyone
it?
hear of this? Yeah. Okay.
Okay, you guys should definitely go. I was thinking just for the summer school student, we can probably arrange like escape rooms if you guys want to do together. Like a team building activity, really. I don't know if you want the advisors to be there. Maybe we'll just book it and let you guys do it. Because then otherwise you just, it might be a bit tricky to say, hey, advisor, you terrible escape room. Just stop messing around with the clues.
Maybe once we can go all together for dinner, out for dinner.
With this crowd.
It's not easy not to.
It's a lot of people.
It's a lot of people. I was thinking maybe bowling.
Oh, that's cool.
Bowling is not going to kill anyone usually. I think we can fit everybody. That's another reason why I suggested bowling. Anything else you guys want to suggest for fun activity? And you guys should do it yourself. Like, we're not going to watch over you. You're adults. I tell that to my 8-year-old, so. Anything else? Do you know everyone's names? No, okay. Why don't we go around with the introduction again before we run off? I think we
Shirley,
already
I have a question real quick.
Yes.
If we organize a social event ourselves, can we get it expensed?
Depending on what your social event is. I mean, New York can get very expensive. So, I mean, I've seen people.
Within reason, possibly.
Possibly.
Reasonable.
You
If
might
you're
want
gonna like go out and blow all your money at a bar, then no, we're probably not gonna cover that.
Yeah, but if you want to organize the bowling trip or escape room trip, let us know beforehand. We can just pay for it and you guys can go without us. I think that is reasonable. Yeah, but if you want to organize something much more interesting than bowling, then maybe not. But if you throw an axe at people, at this axe throwing, which is all in rage, I don't know who's responsible for the insurance if anything happens.
I can explain it.
You said people didn't know.
Okay. All right, let's go around with the
No,
introduction of the
people that be like,
names.
people that
I'm
work.
Shirley Ho. I'll start
Oh,
first.
okay.
I'm a group leader,
No, a lot of
SCCA
people don't
here.
know this.
You guys can keep talking. I have joint appointment at NYU and also at Center for Data Science and Physics, and also I'm visiting appointment at Princeton. Also still have an appointment in Carnegie Mellon where I got my tenure. I have 4 appointments. Natalie.
I'm Natalie. I'm a postdoc here. I did my PhD at CMU, so
do they have
that's
to be
a
full,
fun
right?
connection.
No, they don't. Nothing worth trying.
I work on genomic stuff.
Missima, I'm from the University of the Western Cape. I'm doing my master's.
I'm Elena. I'm from Munich, and here I'm affiliated to CCA.
I'm Thomas. I'm also from Munich, and I'm also affiliated with the CCA here.
You don't have to say which one you're affiliated with if you don't want to.
I'm Lindsay, and I'm a student at Rutgers University in New Jersey.
I'm David. I'm from the University of Amsterdam.
My
You
name
guys
is
want to say what year are you or like?
Just started my 3rd year.
Cool.
my name is Caesar. I just finished my first year of PhD at Stanford.
I am Akiro. I'm from NYU. I work here at CCN.
I'm Jaime. I'm from Colombia, but I work here at Columbia, and I'm in my 1st year.
I'm Arthur. Oh,
We missed
sorry,
one.
I didn't see all the
Then I won't let you speak.
I'm Leo. I'm a 4th year at Humboldt University, and
yeah, I'm Arthur. I'm finally a master's student from Munich.
Hey, I'm Fabian, University of Melbourne, and 3rd year PhD student.
I'm Amaya. I'm not a PhD student yet, but I will be in the fall at MIT.
I'm Andrew. I'm a 4th year PhD student at Berkeley.
At where?
At Berkeley.
Oh, cool.
I'm Matthias. I'm in final year of my master in Vienna at the University of Vienna.
I'm Mahalet. I'm going into my 2nd year at Stanford.
I'm Roy. I'm in my 1st year in the Hebrew University.
I'm Michael. I'm a 1st year PhD student at the Ecole Polytechnique.
Cool.
I'm Domenico. I'm bachelor student.
You're just really young at heart.
I'm assistant professor at the University of Bologna and a visiting scholar here for now 1 year, 1 month. I work in quantum things.
All right, thank you. Let us know if you want to organize some activities. I will send along the slides, promise, hopefully today. But we are going for a Korean barbecue later for my whole group, so I will be like later tonight. Anything else, let us know, okay? We're around.
Like it.
All right,
You work with
see you guys.
Korean barbecue.